GC as well as several others because of double steel stud with the acoustic requirements on the demising walls versus the speed of the way these exterior walls went up. And it is 80% of the 50 plus theaters that I've been a part of. We do get the demising walls because of the acoustical rating of the ICF. So with that being said, I'm just thrilled everybody's here and we got you off the bus and sitting down and dinner's coming. Appreciate you a ton. Look forward to tomorrow and enjoy the movie. Enjoy the movie. We're gonna get it started.
Thanks, Randy. Thank you, Randy.
Feel free to ask questions as well. We want this to be interactive. This whole thing we call it a roundtable event. The whole purpose of that is not just sitting and listening necessarily, but also engaging and discussing with all your peers here. And we will try to have some breaks here and there where we can kind of network, mix with people you don't know, and spread the joy. So to start things off, really, just wanted to thank our sponsors. So obviously I'm with Builder Strength and NRMCA, but the sponsors of the event, California Nevada Cement Association, CalCima, California Construction and Industrial Materials Association, and also ICFMA. So thank you for your support, those of you that are here. One thing with NRMCA specifically, I think if you were here last night, you saw kind of the general breakdown of our approach to Builder Strength in California. So Builder Strength is the NRMCA's promotion team and plan within the nation. It's all focused around communicating, advocating, and promoting and connecting. I'm part of the promotion side of things, and connecting is kind of what we're doing here today with the roundtable. Keeping things moving forward, if you're not familiar with our team, this is kind of the layout here throughout the country. So obviously if you're within the Pacific market, we have Patrick Matsche here, and me in the California market, and also Chris Dagosta, wherever he is, hiding somewhere up there he is. So he's down in kind of the Midwest area. So we're here today to support you as well. If you have anything, the big purpose and our focus is to connect you guys with the resources and tools to make concrete successful on your projects within these states. One thing I really wanted to touch on, not so much specific to ICF today, but just something that we're doing in California specifically is has a strong emphasis on sustainability. So I wanted to throw this up here. Just, if you're haven't had to cross that bridge yet on sustainability, it is something that is kind of coming down the pipe in terms of legislation, things that we've been seeing in the markets, not just California, but also nationally. Trends are going up, and we're seeing just a lot of volume within these legislation opportunities that will ultimately impact future projects and the projects we're working on now. Specification trends, same thing here. We see this all the time within specifications. Architects are starting to ask for EPDs, other sustainable benefits, and things that are ultimately going to get them towards their goals of, Architecture 2030, which is net zero by 2030. California has their own in-house California 2045. Structural Engineers Associations, they have their commitment to SE 2050. So they're all working towards the goal of ultimately getting to net zero. And how to accomplish that, that is the big question these days. And those are the resources that we have available to you guys to ultimately help get you there with concrete specifically. At NRMCA, kind of what we're doing these days, we offer some of the things that we offer are specification reviews. So if you have, if you're an architect or a structural engineer, or are working with architects or structural engineers that have need a little bit of assistance in understanding how we can better improve specifications to make a project a little more friendly on the actual execution of the project, not handcuffing ourselves, making sure that we're all ultimately working towards the same goal of whether it's sustainable solutions or just a more amenable design process. We are able to help review and mark up specifications. We have our specification guide available to all of you and the general industry on our website. I definitely encourage you to check that out and give that a read. It works towards different things from talking about carbon budgets, if we're talking about sustainability, as well as getting away from prescriptive specifications and towards performance-based specifications.
And that info is on your website, you just said?
Yeah, so our specification guide is available on there. We do have a amended one that is focused on embodied carbon. It's not on the website, but I can distribute that to you. That is some of the...
Is it downloadable?
Yeah, it's a full guide on there. And it shows the general specification commentary, kind of similar to it, so easy to read. Next up, just design assistance. There's a lot of things that we can do, and we offer from full LCA support, looking at EPDs and resiliency within structures, ultimately highlighting different and comparing different superstructural envelopes from concrete to wood to steel, also looking at sustainability benefits, things of that nature, and just ultimately connecting local producers to these projects. So if you're in certain markets, a big question we've seen is a lot of people having problems with, well, is that available where my project's going to be? I don't know, so I don't want to be, too explicit or specific on what I'm doing. Well, we at the NRMCA can help you connect with local producers. So if you have a project going on in the LA market, we can connect you with the local producers and make sure that things are being done and steered toward in the right direction for what they're capable of doing. Design center recommendations, if you haven't, I think we had a few laid out here. We do design assistance reports. Things looking at an actual project, taking plans, specifications, actually looking at a comparative analysis between, say, a wood frame to a concrete frame, to a steel frame, whatever it may be, looking at the operational costs, looking at the actual construction and estimating costs for producing that building, also trying to incorporate more things around sustainability, things of that nature, looking at assemblies, all types of stuff. So we do have these services where we can actually take your plans and we will in-house do a full-scale analysis through our in-house architects and engineers and provide that to you free of charge.
So, question?
Yeah.
In order to take advantage of that, do we need to actually design the job both ways?
It can be a napkin sketch or conceptual concept. We have standardized, if you're trying to do a multi-family building or a hotel of some sort, it's 100,000 square feet, we can take things we've done in the past and we have standardized templates that we can use to at least get the ball rolling. And as the process goes along, get a little more refined, we can hone in on what's actually within that. So
How long will it usually take?
Turnaround could be 2 to 4 weeks typically, sometimes a little longer depending on the season, but more or less we have a dedicated team towards doing that. So that's their whole job, is trying to think these things out. So by all means, reach out. We can tell you kind of a real-time estimate, but that's the typical there.
And these are estimators who understand.
Yeah, they're using
they're
using RS means, things of that nature, and obviously they're not explicit experts just in that specific market. So there's a lot of some relativity comparing between the estimates, but we can also, like I said, break it out to assemblies, get more specific at that, per square foot per wall for certain aspects of the building, and it'll at least hone in on the cost differential. And lastly, just the education and roundtable on site tour events. So obviously, site tours that we're doing today and roundtable today, but we also do a lot of in-house and out-house education efforts from lunch and learns, things of that nature. So if you, within your own entities and firms or partners, are looking for anything concrete related, whether it's Concrete 101, sustainability, ICF, we're all here to support you guys. Or if it's other people that you're working with in the industry that can benefit from knowing a little more about concrete, we're here for you guys. So keep that in mind. That being said, I want to move this along here. I think.
Hey, Brandon.
Yeah.
This is Lionel Lemay here. There were questions about the design assistance report. I happened to print out, before I came, just a couple of examples
Yeah.
of what they look like. And so I'm just going to pass it around.
Yeah.
Take a look and then just pass it to the next person. You get an idea of it. This is just one example. We can do all sorts of different permutations of this report based on what your needs are.
Yeah, it's hard to encapsulate it in one single document because there's ones that are very focused on the construction estimating, and other ones focused on other aspects of it, but it gives you a little taste of what we can do.
Is that one of the brochures that the information staff said were up there?
Yeah, we had a few things that were up there. We had
Same thing that
that specific one's a little thicker, so just take a look at it. Yeah. I think we have another design report that was put together as an informational thing on Portland limestone and cement, and that's something that was being handed out as well. So a few different things there. So kind of next up, I think we have Steve Geltema. I screwed up, but so he's with the Superior guys, basically looking at being our host and whatnot. He was actually in charge of building the Amenable facility, or the execution of it, I believe, which broke ground in 2001 or so. Yeah. Okay. It was a while ago. So, but yeah, and I'll see.
Can we give Brandon a hand? New dad, keep down. Thank you, Brandon. Steve? Yes.
Good morning, everyone. So my name is Steve Geltema. I moved here from the Midwest 7 years ago. But I've been a part of Meadowbrook Village since 2008. Through the interior design firm I used to work for out of Michigan. And so I've come to know the Broward family really well, know their passion behind this whole campus. This is a benevolent offering to the community. This is a nonprofit product. And so every effort was put into making a very long-lasting project, and that's how we came to ICF at the end for the last building. So as I was at the event last night and seeing what NRMCA is all about, I noticed the connect part. I want this to be a situation where I'm just sharing information, and I want you to ask questions if something I say resonates with you, if you have some idea, or I want to understand the concept some more. My perspective is going to be, as a project superintendent with ICF, sharing with you the challenges, the opportunities, the things that we move through, how to work with your structural engineer, because he's going to become your best friend or your worst enemy, depending on how you handle that situation. And you have to handle that situation with this product. There's a lot that goes into it. Our building is really different from what the cinema was. We have over 100 exterior penetrations for windows and doors. We wanted every apartment to have a lot of daylight. And as a result of that, there's a lot more challenges with the ICF block, with any construction, because of the structural implications around those openings. So, as a beginning, Mr. Brower, he was here a few minutes ago. Anyways, his son, one of his sons, built a home with insulated concrete forms, I don't know, mid-2000s. And Jack really liked what he saw, and as he was planning this new building, he was at World of Concrete and ran into Randy and started asking questions, and Randy has lots of answers. Anyway, so the decision was made to use that product, and that was what the architect started out with. There are a lot of things to consider when you're using this material. Of most importance when you're starting out, you have a 2 5/8 inch thick wall. Start looking at your plans. You want to make sure you're using not face of foam, but face of concrete as your dimension point, because that's going to be solid, rigid. It is what it is. Your foam could condense, could be crushed. Face of concrete is how you build a building. Anyways, the decision was made to use this product because of its longevity. You put a building together like this, you're not dealing with termites, you're not dealing with dry rot, you're not dealing with elements. This is a solid building, and we were just thrilled with how it went together, with the overlay of contractors we had on site and how everything came to be. You can see the intricacy of our building as we bumped in and out to accommodate certain facets of the building, the funny angles. There was just a lot to pulling this product together. We had a great contractor on site, ton of construction that worked through it all. And we started out with a subterranean garage. We had 12-inch thick concrete, which makes a 17, almost 18-inch wide wall down below with the insulation. And we were just really happy with how that all came together and the structure provided. And we needed that much structure because our first floor deck is a PT deck, post-tension. And we're going to offset our columns, so we had plenty of space to drive in and park. And then carried our corridor walls in through ICF all the way up through the building. I don't know if we have a first floor plan that would show that. We can see it when we walk through the building later today. Anyways, that post-tension deck gave us a lot of opportunity in design to make a building that served as a garage because we needed the parking space on campus, and then offered us the ability to bring those interior walls in and offer the noise reduction we wanted in the main part of the building for structure, as well as noise reduction for all the people that live there. As you can see, there is a lot of rebar, all the verticals, at every window opening, every door opening. There are 4 verts surrounded by what's called a stirrup. It's a round piece of rebar going up and down every 2 inches. A real challenge to tie all that rebar and wire together. And as we moved on to our next building, we used a different contractor, Nibbling Construction, and they really got crafty with how to assemble that product. Rather than try and reach down in with 8-foot or 10-foot verts and tie those rings every 2 inches. They just took the foam and cut the foam out of the way, pre-built their stirrup columns, stood them in place. It was easy for the inspector to see everything, and then we just put the form back in place. Remember, the concrete is just a form, the foam is just a foam. You can hold it together with the plywood, and I think we can see that on some of the pictures, but strapping to where the collapse indentation is, you hold that foam together around any opening against any window buck or door buck, and you have a great solid product. So there's ways to step around this material to make it come together easier, to make it assemble quicker. This is a very different project as compared to the theater last night, which they just want big straight walls with a lot of insulation for noise, not any windows because they don't need them, and a few doors to get in and out. All of our window and door butts, we use LVL material. We treated it all for pest control and water control, anything. And we would cut it to width, outside to outside, and then we would insert J-hooks, pre-assemble them all. So I had a carpenter on the end of the campus assembling all them. And when it was time to do first floor, everything was delivered to the site, stood up in place, J-hooks installed, ready to go. And it just made a real quick process of bringing that all together. And then it's poured in place. And once we were done and ready to install doors and windows, we had nail into, and it was super strong because it's LVL material.
Hey Steve, what's that picture on the lower right? Explain that.
This here?
Yeah.
So this is our elevator shaft, which requirement can't be anything flammable inside the shaft. So we had to set up scaffolding, go top to bottom, and peel all the foam and all of the binding, strip the joint or plastic out of the way. Yeah.
Calling that a better way to go in lieu of doing CMU?
Yes.
Peeling off the-
Yeah, because 8-inch CMU, one, you're not insulated, so you
Right.
still have to do insulation in addition to that. And 8-inch CMU,
No, for your elevator wells.
well, so it's still part of our structure, so we needed it for, to land everything on, and we wanted to keep it to 8-inch wall with the foam on the outside, so we still had that insulated noise from the elevator not operating and sounding next to the apartments next to it. So it worked well, it integrated together, it kept one contractor going as opposed to two different contractors and then trying to make that together.
What was the easiest way that you found to peel the foam back off?
We would go in with sawzalls, take a few cuts like this, and we just use a spud. And just start scraping, and once you had a void of this wide, it just is an easy pop, because by the time you get back to it, you're just popping this and this connection, the
Yeah.
foam peels off.
Real quick.
So, you get a long way.
It's so smooth on the inside.
Yeah.
It didn't.
There's a little bit of bite to the concrete, but once it starts going, it just moves right.
Got it.
So when you're talking about installing these pre-tied column cages, essentially, you cut foam, cut the
We
plastic spreaders,
cut it off and cut it off because you need access to it, yes.
stood the column cage, and then just tied the foam back to it. So all the internal depths you got rid of over the width of the
Right.
structural level.
Yep. Yes.
Did you guys look at all for the elevator shafts using more of a single-sided system versus the traditional
I don't know
ICF?
that it was available, but we didn't look at that, no. It wasn't something.
We didn't offer it. The ICF industry single-sided solutions are still not great. They're getting better, but they're still not great.
Do you have any photos or videos of the post-tension slab that you were referring to?
I sent a few, but I don't know that they were integrated in the,
Yeah, we can get to it.
the other, I would say, very important feature for all this is if you're going to use post-tension, is tie that all into one contractor if possible. So that you're getting so we used cold form steel trusses on the roof, hand deck with steel bar joists for 4 levels, obviously the cable for the PT deck. The ICF contractors installed all the rebar, we supplied it just because of our connections with that product. But on this particular project, we were unaware that our one contractor was capable of doing it all, and so we split it up between two contractors. It just made it a little bit more difficult to tie them over. Randy, you have the connection for the floors, the seal. So we use a seed channel at all of our floor decks along the DT.
There on the floor, right?
So right here, we mounted seed channel around the perimeter of all the exterior and the corridor walls, area of the floor decks above. And then off of that, there was a bracket that was about a 6-inch wide bracket that the steel bar joist rested on right here. All of that fastening was done after the pour. So we would cut the foam out of the way, and then we use Titan HD anchors, and we would elevate the beam on a couple of crank jacks, get them up in the air. We used a laser level to make sure everything was right on level. Pre-drilled a couple holes, set a couple anchors, and the crew moved on to the next one. And then we just had the crew follow behind and do all the drilling. And we burned through a few rebar cutting bits, but that's part of the game. It's a lot easier afterwards than trying to set templates at the beginning.
Yeah, that was my next question.
Yeah. Now, there were some areas where templates went in on some big beams we had to do, and that's just another part of working with the contractor. We had two different contractors that we used. The second one was more willing to set the templates themselves. The first time around, it was left in our hands to do. So just nice that it's integrated all with the ICF contractor as far as we're concerned. Makes everything more even flow. Not that it's putting the responsibility on them, but as they're building the wall, they can cut the windows, set the template, be ready to go on the floor. One other thing that I'd like to point out about the walls, if you looked at those walls yesterday and how straight and true they are, on occasion you're going to have a wall that does belly a little bit. There's just a lot of pressure going on. What's really nice about this product is you can come in with a plane and just shave that foam down a little bit and get it back to plumb, and you're not losing much material there. You know, you've got inside and outside foam. There's a lot of insulation there. So be able to shave a little bit off, make it back to a flat wall is a nice piece to this whole concept.
It really doesn't sway out a lot.
No, I mean, that's part of your bracing. But there's, we have one occasion on one wall where we had a little bit of belly and they corrected it by just planing that wall down a little bit.
Do you find it if you go up a certain amount of courses and bore?
We didn't do, yeah, I was shocked to hear the height that XL Masonry was going yesterday. We were going 12-foot walls and we were doing 3 lifts. So they were pouring around 4 feet. About an hour later, we had enough pour that we had that kind of time in between, but they were doing 4-foot lifts to get to the 12-foot.
And you still found that it kind of bubbled out a little bit?
Just, like I said, on one wall, on this whole building, on one floor, one wall, we got a little bit of a problem. So.
And it's supposed to be bracing, loose bracing, not,
Yes, sir.
When you talk about planing the high spots, if you get a bow, like, are you talking about like with an electric hand plane, or
They use like
rasp?
they use this like a wood rasp, and they just rasped it with that. I mean, it came out.
As opposed, like if you got a corner that's out of plumb, can you set a metal straight edge and then use the hot wire, 10, 12 feet long or whatever, or is there a limit to how long you can do a hot wire cutter?
You're asking the wrong person on that. And in my opinion, this was our favorite tool for anything we did for cutting as far as getting into any other product. I hadn't seen this one yet. It has a roller wheel, so it keeps the tip off the concrete. But as I was talking to Randy about it yesterday, that makes the biggest mess on the job site. Just foam's flying everywhere, and you obviously want to control that, especially if you're in a city setting. You're going to get nailed by your inspectors. So we never had a whole lot of success with the hot wire, but Randy's point yesterday to me about that was if you are in a setting where you have to be very careful with any of your discharge waste, that's a way to cut it. You're not going to have any foam pellets falling anywhere because you're just melting foam and getting it out of the way. We did use the iron some in a few areas where we had tight corners. There is convenience to it, but our favorite tool was Sawzall with a blade and just stay right on top of the concrete, make your quick cuts, chip it out. All of our electrical, we did drops down to from our interstitial space above the floor, or above the ceiling, below the upper floor. Dropped everything down in conduit, and then just ran MC cable up above. At the top of the wall, just there was where's the trusses? At the top of the wall, then we just used the structural engineer designed a long flat plate with J-hooks that was set right up the concrete was poured. So we had a weldable surface right at the top of the wall and fastened all of our joists to them. And like I said, we used post-form steel joists. Because of the complexity of our building, we did GPS coordinates for our truss manufacturer so that he had what he needed to get the trusses to come together on that complex roof. We, as you can see, have a parapet system all up in here, and then we added solar electric to the 4 wings and solar thermal in the middle. And we're in California, make use of what's out there as far as energy savings and in space. So we tie a lot into a very small footprint on this building. It's 66 units. The only real common space are corridors and a lobby on the main floor and then a subterranean garage. And as Randy mentioned, I crunched some numbers the last couple of days to compare basically per household what our existing building on campus was that was built in 2008. That has 2x6, 3x6 exterior walls, long cellulose insulation. It's airtight. And then I compared it to what this building is with the foam inside and outside of the concrete. Per home cost for gas and electric, right around, this is for the month of October, $168 a month in that building. And I took into account about 20%. I took off the top of that because there's more common space in this building. So I got down to what I thought was pretty accurate, livable space for residents over there. And in the new building, doing the same thing, and I accounted for the solar beam we have over there because we have a fair amount of solar in there. I subtracted that from the number. We were at $107.65 per home over there. So $168 per home over here, monthly cost for utilities, $107, $108 over here for monthly cost for utilities. That's a 33% cut, $165.
Within the same year.
Same month, same year.
Per home.
And those are duplexes, right? They look like they're duplexes, or are they single units?
They're all single units in this building, yeah.
But they're all within the same, they're all within the same.
Yes, yes.
So it'd be different than a single family residence? or-
Correct, yeah, I just tried to compare one large building to another large building, what the operating costs were for the resident there.
Do we get to go inside?
Yeah, so when we tour the building, I like to do a walk around the perimeter just to see what it looks like from the outside, how we use brick and cement siding in the exterior. Walk down to the garage so you can see how we played with PG deck and what that did for us down there. And we'll come up into the main lobby. And I have one apartment we can go into on the main floor because it's unoccupied. So you can see inside and outside and what we did fully going together.
So as you look out the front doors of this building, you're looking at that we're going to tour. It's right next door.
I'd like to note one other thing too before our questions, and that is when we were going through the building, it was very, very important to the owner that we kept noise down as much as possible from one apartment to the next. I mean, these are people's homes. We're trying to think of them as they're the consumer using the product. We had no issue with exterior noise. We're on a busy street behind us. You know, we're on a campus. There's construction things going on. We were trying to figure out what to do, how to cut down on that noise transferring through demising walls. Our demising walls were 2x4 construction, steel, offset, 8-inch wide overall, so there was a gap in between. We tried fiberglass, we tried blown-in foam, up the wall and across the ceiling, and we did cellulose packed. Far and away, cellulose was the best product to use. The next closest was foam, and we had a 10 decibel difference. We had our own sound meter in there from foam to cellulose, from one room to the next. And it was at the critical point where you're going from mid-40s to mid-50s, where you're really dropping that noise down that you can transfer that is noticeable by ear. So it was really important to us, and it was a fun little project to do, and it netted great results for us.
So the cellulose, does that work where you put the netting on each side of the wall and make a little hole in it and then fill it
So,
with
yes, that's one way. The contractor we used, they have a different system that actually puts just a little bit of mist in with it. So drywall one side, and they blow it in complete, and then you let it dry for 2 days, and then you can drywall the other side. So you're cutting that whole, especially with steel studs, how you're gonna keep the netting in place.
Right.
That was the way to go about that. And then in the interstitial space, about the 3-foot space up above, because our ceilings are all 9 foot to the next floor level at 12 foot, we did exterior rated 20, whatever you need for normal fiberglass roll for a ceiling. We use that as our sound batting as well then on all the levels, and then for the upper level above, below the roof line. So that's how we really cut down our noise. Our walls were, because they're demising walls, floor to ceiling, packed with that cellulose. Lastly, not that I'm talking about this in the proper order, but as you're looking at your MEPs through your building, it's really important to make sure that you plan a window to penetrate each apartment to get those MEPs in and out of there. There's a lot of cabling and a lot of plumbing that has to go in and out. Make it through one small window with just one window you need to worry about then as far as fireproofing. That's obviously a critical concern in California. And I would strongly suggest that you team up with 3M and have someone come on site and train someone from each one of your trades. And that's what we did. An electrician trained, a plumber trained, an HVAC guy trained, and a couple of my own guys trained. And we did a lot of our own fireproofing. And that way we were in control of it. We were on top of it when the penetrations were complete. And it made a big difference in getting the job done the way we wanted it done. Yes?
Did you use like an air water barrier at all on the outside or?
Yes, well, down below on subterranean, we had a contractor come in and we did a full waterproofing membrane on the foam down there. And then up above, we used, behind all the siding, we were using just a normal tie back. It was a brand, I think, maybe tie power we used on the building. So we did wrap the foam as well. I was told it wasn't necessary, but it was on our plans, and therefore we followed through on it with the city of Escondido building. I was expecting that.
the manufacturers, I think, will say that the ICFs are in our area because of the concrete inside, right? So you don't need to
You
tie
don't need,
anything
but
up.
we did do it.
Yeah.
And we flashed all our windows accordingly, everything was done to code, if it was typical stuff.
And then did you fur out on the inside, or did you just?
No, the inside was straight drywall right on top of it, so that's the beauty of it with these strips are 8 inches, and then with the embossed on here, that's basically the width of a stud, and you screw drywall right onto that. You just need a longer screw, and Randy swears that the holding power of that is stronger than screwing it with a 2x4.
But I like that.
How deep below the surface of the insulation is the thing?
It's 3/4 of an inch buried in, so you just need that 3/4 for your normal screw length. Yes?
Question. So being on the owner side, my design team is always changing things last minute. So, I mean, obviously, I mean, it's the same thing ICF as with, you know, a precast product or any other concrete wall product. Is there any opportunity for a chase or some kind of built-in insurance so that you can add electrical or AV, or as things potentially could change? Is there any opportunity to increase some flexibility for future owner changes with this system, given instead of, you know, a precast?
So probably your biggest challenge is going to, for us, was the fact we have a PET deck. You can't penetrate. If you saw the picture of the weave of cables on that deck, I kid you not, there were spaces that were less than 2 inches in between cables. So there were a few chases that went through that deck, a couple of large ones we used for venting as well as some electrical and plumbing runs. Most of the stuff was obviously you need to pre-design that so that you're ready to go and know whether all your sleeves need to be and your forms. From there on up, you've got some space. Again, this is 2 5/8 inch. You've got a fair amount of room behind the drywall if you need to get up and down. For electrical or plumbing, for HVAC, more of a challenge, I suppose. We have a few closets that were designed for that extra stuff too, and we made use of that. Our upper floors, we would just obviously core another hole. But through our electrical rooms, we also had some 4-inch sleeves and a couple spares put in. We tried to think ahead for the future as well. And as it was mentioned last night, the insulated concrete foam is a great insulator for cellular as well. And an aspect that we had to face at the end was first responders, the radios weren't working in the building. So we had to add an antenna in the building that spread out on each floor and then up to the roof. And it was an expensive add, but it was necessary. So that's part of what needs to be considered too, something like this. They're give and take.
Did you use ICF for anything else other than perimeter walls? Did you use it for any of the interior demising walls?
Interior corridor walls were ICF as well. So subterranean was all 12-inch walls because we're supporting that deck. Perimeter walls above grade were 8-inch, and then the interior corridor walls were all 6. Elevator shaft, I believe, was 8 inches because we carried the weight of the elevator car. And we had some other weight-bearing beams coming in resting on that, so that was a little bit different. That was part of the design from structural engineering.
All right, we're gonna take 10 minutes. I'm gonna send Steve to you. So we should do a little networking and ask some questions. We'll flip over to the next presenter. All right, Brandon, you're in charge. Yeah, thank you, Steve.
Huge advocate for ICF, has done a lot in the industry in terms of ICF construction all throughout, particularly Utah. He comes to us as with his firm, like I said, Design with Architects, with offices in Logan and Salt Lake City, where they kind of post Eagle Creek Design, where their client-led design methodology approach has kept them in business for over 130 years. Stephen himself has presented at the Colorado Association of School Boards and Minnesota Concrete Council on ICFs. He's also presented with Build with Strength at many different events as well. So he comes to us, like I said, with a lot of experience, and looking forward to what he has to say.
Thanks, everybody. It's good to be here. I've given this presentation before, so I hope I can add some flair to it. I told Randy this morning I was going to wear a suit, but I'm still recovering from Thanksgiving. My shirt didn't fit. My suit fits. My shirt didn't fit. So part of my casual appearance. But that's kind of the way I am. I shoot from the hip, and I'm a pretty easygoing person. I don't get my feathers ruffled very easily, but I'm a pretty common sense person as well. I'm originally from North Carolina, from the South. We're pretty laid back kind of people. And anyway, so that's a little bit about me. So the title of this is How Keeping Concrete Hot Can Help You Understand the Benefits of Insulated Concrete Forms. Designed by Architects, like he said, next year will be our 130th anniversary. We're the oldest continuously operating architecture firm west of the Mississippi, which is kind of cool to be able to say that. Talking about Swiss architect Carlsbad. This is the old main building at Utah State University, so one of the pharmacies done. So we're just trying to continue a legacy of good design. This is my family. After I took a Disneyland, I couldn't grow a beard, but after rubbing shoulders with that guy, things started to happen for me. So this is my little quiver of kids. So here's our objectives for this presentation. Why is ICF a good tool for achieving net zero energy design? Benefits and cons and attributes of ICFs. Some details, rules of thumb, and some lessons learned. Understanding the benefits and properties of thermal mass. We'll talk about our case study. And the history of ICF use by design with architects, just some of the problems with that. So net zero energy, what is it? When a building produces as much energy as it consumes. That's right. I actually, when I reread this presentation, I had it all the way around, like, that's not the case. You have to produce as much energy as you consume at least, because if you overproduce, it just benefits everything else. So what does net zero really mean? When a building is master planned, where when fully realized, the components in place has the ability to produce as much energy as it consumes. So, like for instance, we do a lot of schools in our firm, and we have some very conservative budget-minded people in the districts that we work with. And some of the strategies that to achieve net zero, they're not on board with yet. So we try to master plan our schools to be adapted down the road to be able to approach net zero energy. Some of the components of a net zero energy building, passive energy source, whether that be photovoltaics, wind power, hydroelectric power, or geothermal exchange. Mechanical electrical systems, you have ground source heat pumps, fluid exchangers, covered heat exchangers in mechanical systems. Evaporative cooling is a really inexpensive way of cooling. LED light technology is really, I think that's one of the biggest things that has helped us get to the net zero threshold. And also just maintenance and rules for people who are using the building on being conscious about what you plug into the wall. Whether your computer's on or there's a lot of things that maintenance strategy you can deal with. So what are the components that make up the net zero building energy? So one of the most important components is that envelope. Because if you don't have a good envelope, then the loss is there. And here's a good quote. Everyone instinctively knows that when you go outside on a cold day, you must zip your coat, stay warm. It doesn't matter how thick the coat is, if it's left open, your body heat will leak out. Same is true with building insulation, no matter its R value of thermal performance. If insulation isn't continuous through the building envelope, it's like a zip coat, like an unzipped coat, wasting energy and money. I'm from northern Utah, and our climate changes from the south of Utah to the north, and almost Fort Idaho, it gets really cold where I live. And being from North Carolina, the coast of North Carolina, I really know now, living in the mountains of the mountain valleys of Utah, that really does hold true. So the first step is in this process of determining your climate zone. Here in California, I think we're climate zone 3. Going into climate zone 6. As soon as you get on our it's on climate zone 5. So there's some different things that puts in front of you. Because your climate zone depends on what your required continuous insulation value is on your building. If you look at the IECC, which is part of the IBC manuals, it'll tell you what R value you need for your cavity insulation, so if you have a stud wall, and then what kind of outsulation you need R value. For instance, climate zone 6, if you look here for Utah, in a commercial project, on a mass wall, you need an R of 15.2 if you're just doing continuous. Metal frame, you need an R13, and cavity is 7.5 on the continuous. And now a continuous insulation component is required by the code on all commercial buildings. So here's some examples of some common approaches to continuous insulation, and most have to do with a cavity and a continuous component. This one on the left, that's just a standard residential stud wall with a continuous insulation board prior to installing siding. Same thing on the commercial side, if you have or residential, they're doing metal studs residential as well. Cavity insulation, continuous, and then on a CMU, you're doing continuous with a furring and then a chipboard to add your final product. So has anyone ever had this happen to one of your beverages? Okay. So what's happening? Is the beverage hot or is it cold? It's cold because the air and the moisture and air condenses to the cold surface, correct? So how do you fix that? You give it a little huggy. And what does that cause for that? That becomes an insulated form. Anyone ever had this? It's Christmas time coming around. That happens in Utah, especially if you don't have insulated windows. How do you fix that? You add more insulation. You add more layers. It's kind of like, if you're from the Midwest, the cold air is a lot different than the dry mountain air. You can use one layer and get away with it, but you have to layer up. Midwest, North Carolina too when it gets cold. So to make windows work, you just add another layer of glass and then you put an inert gas in there like argon. It's heavier than air, so it creates an insulation barrier. So talk about the same concept. So let's talk more about beverages. Anyone ever have one of these? Why do they put a handle on it? I mean, isn't your hand big enough to hold a mug? So you don't burn your hand, because that's not a very good insulator. But it's great for this. I mean, if it's a cold day, you're like, oh, warm my hands up. That's the best thing to have, right? Anyone ever seen one of these? There's a gal in my office who has one of these every day. She brings her coffee in one of these thermoses. 3 o'clock in the afternoon, she's pouring her last little bit, and it's still piping hot. Still steaming, right? Because if you look at the label on the thermos, it says 24 hours of cold or 24 hours of heat. That's because of the insulation there. So what's this? Same thing as this. You might say that's a cup of coffee or a cup of hot chocolate. No, it's a calorimeter. When I was in high school, which I barely made it out of, by the way, I wasn't a very good student. One of the things I did learn in high school in physics was a calorimeter is a vessel used to measure the amount of gain of heat of a chemical reaction or cooling a chemical reaction. But a styrofoam cup is a cheap calorimeter. And why is that? Because it's such a good insulator. It doesn't lose a lot of heat from this vessel. So that is an ICF. It is an insulated coffee form or a chocolate form. Nonetheless, it is an envelope that is preserving the thermal mass of that reservoir. This also is an ICF. That's the same one that's right here. So some questions that are frequently asked. What stands for insulated concrete forms? What kind of projects can you use ICFs for? Just about anything. It's becoming more prevalent in the commercial side of things. I think it started out more as a residential product, but the commercial side of things is catching on. What kind of finishes can go on ICF? Anything you want, really. There's really no limit to what you can use. Sometimes you have to do some installation of some other components to the face of an ICF to accept different materials, but really it can take anything. Like if it's an EAF system, which is exterior insulated and finished system, since the foam is already provided in the spec, it's called TAS, which is textured acrylic finished system, which is the acrylic component of EAFs, just technically speaking. How tall can you go with ICF? Well, I asked Foxbox to answer this question, and this is their quote. We built walls as tall as 53 feet, just the floor and the roof high. Tallest building is 22 stories and 200 feet, 250 feet tall today. Pretty close.
It's higher now.
Is it? Okay, I'll have to open this slide. How fast is it to install? It really depends. I'll show you the projects that we've worked on. They don't go as fast as movie theaters, I'll tell you that. Movie theaters do really go fast, but it depends on a lot of different factors. It depends on your weather, it depends on your installer, it depends on the experience of your installer, because we've had some projects where we actually had to train them to do ICFs. So it really does depend. So what trades have installation crews? A lot of times masons typically do it just because they already have the scaffolding. Carpenters can do it, even concrete installers can install ICFs. Up to 60% savings in energy efficiency, and you can downsize your mechanical equipment by 30%. ICFs qualify for lead points. 6 to 19 points is what you can gain from using ICFs. In our firm, we design the lead standards, but we don't really apply for the $25,000 plaque that says, yes, we're lead. I think any architect worth their salt should be able to design within the standards of sustainability if the budget allows it. And R value ICFs. Now this is kind of a tricky one. The R factor for the EPS fund with ICF, so we have 5 1/4, 2 5/8 on each side. at 4.5 R value per inch, right about R23. But that doesn't even take into account the thermal mass, and that's the beauty of the whole ICF thing, and that's what I'm trying to get home.
So, Steve,
Yes,
that brings up, I think, an important question. As I've kind of studied about ICFs, trying to get more familiar with it, there's a kind of a shortfall in the whole R value measurement because it doesn't measure the ability of a wall to resist heat transmission through the wall. It only looks at one component of the wall. So is this industry developing any kind of a test that is a realistic measure of heat loss?
But I'm going to talk about something.
I'm throwing out a question for the industry. Is there some other measure that we can use? Because if I go to a client and say, it acts like an R36, the client says, yeah, right, you're trying to sell me something.
So I'm going to show you a case study on a 6-inch ICF wall comparison to a 2x6 stove with cavity insulation, which is the typical.
I think it'll be pretty amazing, but how do we get that into the standard?
We'll believe it.
Yeah.
And actually, this case study that I've seen, it's really what causes me to advocate a lot on the energy side of things for this product because of how well it tightens up buildings as far as keeping indoor air temperatures constant. So hold on to your seat there. So starting in January, we're starting our 9th ICF project at our firm. We started back in 2012 with a student housing project in Gunnison, Colorado, which is the highest elevated university in the United States. And they asked us to do a student housing project. Now, I'll get that in a minute. But just some lessons learned on detailing for ICFs. When we did 4 schools, elementary schools up in Idaho Falls. And some of the details up here were new. You can see like here, we cut away foam core precast there. We showed our in-bed plate inside the ICF wall rather than out on the surface. That's not really realistic, not really how that's done, but that's how we detailed it. And we've learned our lessons from that going on. Also, those Idaho Falls schools, we did a hybrid system. So we had CNU block below, wherever it was an indoor space, and then we transitioned to an ICF on top of the CNU block wall, where it went to an outside space. So this is an exterior surface, this is an interior surface. That was just for the architecture of the building. We had built this building before out of CNU. We were converting it from a CNU building to an ICF building, and that's how we determined to make that work. As far as window ducts for ICFs, this was our detail for that elementary school, where we cut out the profile ICF on the front, the left, the block on the back, and then put a wood buck in there. That way we had continuous on the outside, but we had nailers on the inside. And this is before we knew about Fox bucks, because I don't know if they were around at the time, but this is what we had determined to do. Install these screws at the beginning. Actually, this bottom plate here wasn't installed until after it was poured. You see these 2 little nailers here. That way they could pour into the window, and this was installed afterwards. So wood bucks, just like a wood stud in the wall, will create a thermal path into your building. So it's great for nailing, but if you can find a way to do the insulated concrete form bucks that like Fox offers, it'll make you get you a better envelope. So we've determined to use those and figure out how to use those on our exterior envelope, but for any interior ICF walls, we are using wood bucks because it really doesn't matter at that point. So this is how that detail turned out with that wood buck. We had a 4-inch corner off of our veneer that turned in. We cut away the foam so we could close the gap between our window system and that buck. You see the header here. You see how we pull it right there. Essentially, they had to build a framework inside of that buck when they poured it, and then they pulled the frame out, and that was what was left there. So what we've gone to since then is is actually incorrect as well. This actually still listed there. So this is for Roy Junior High School, which is a junior high school we finished about a year ago. The position of your storefront windows in an ICF system, it's got to be far enough back where you can tie into that ICF on the sill. So what we've determined is that if you come back far enough where you have a 1/4 inch overlap between your CNU that returns and the sill, then you have a good sealant joint there up and all around the window. Or you can go to a deeper storefront. We're trying to keep it economical by doing a 4 inch, but you made it to a 6. On a roll-up door, it's good to cut away the foam and install nailers there for attachment, because oftentimes, especially if you're doing the ICF buck, the nailer's not really there to attach the rails for a roll-up door, so you need to add the wood to the concrete. So this is where you could actually, on the interior roll-up door, do that out with an LVL buck, and then install it that way. So you mentioned whoever was presenting before, using LVLs for bucks on the exterior. I think that's a great idea. I think actually the reason why, and maybe Randy knows this better, if you think about a 6 inch ICF core and then add the 5 1/4 of insulation to that thickness is 11 1/4. And that's a nominal thickness width of 2 by 12. So I'm wondering if that's where they started in order to get that first width on the residential side of things. Do you know?
Yeah, the ICF industry, a lot of manufacturers default to nominal widths for,
Okay.
So 2 by 12 was the original buck system for.
Yeah. It just seems like an odd dimension on 2 5/8, but it more than meets the necessary CI for continuous insulation for a mass wall. So I think that's a good happy accident, personally. So this is how we resolve the issue with the 4 inch. So we don't cut back the foam for our sill, and we move our window back far enough to where we have flashing that comes over a precast that is pre-slip, by the way, and then we slip off that way. That way we have a connection from there through our plastic ties in the buck system. Another thing to consider with ICFs is that if you need a 180-degree swinging door, make sure that it's out far enough. If you use a standard 5 3/4 inch frame, it's almost not deep enough to dimple into this concrete. So going with a deeper hull level frame is important. That's also another reason why you would want to maybe use LVLs for your wood bucks, so you have a nailer to go into, so you can shift that door frame where you need to. Also, something to consider. So this is a 10-inch ICF wall that's part of the cafeteria. This is coming out of the cafeteria kitchen. The ADA guidelines require you to, anything even deeper to the door than 8 inches, you have to have your push clearance on that side of the door. This is not needed. So if you're doing hollow metal frames and doors in that thick of a wall, you have to make the opening wider, put a side light, or frame in a secondary wall in order to make sure that works for ADA clearance. Our inspector was gracious enough not to make us do that. That is a requirement. We're doing elementary schools finishing up here in a couple months in Logan, where our office is, and we're actually doing this with thin break on our ICS. We have pre-construction meeting prior to construction, and we told and IMS Masonry has done almost all the projects that we have done ICS with, except for the Idaho schools. And one in Colorado, but the Utah schools, it has been. And we told them, we said, okay, you guys, we're not gonna have a cavity here for an 1 3/4 play. We need you guys to make sure these walls are straight, because what's out of line on your end is gonna telegraph onto our brick, because they're putting up their extra inch of foam for their coursing and applying the brick. We started out with our detail, cutting away the foam and putting a precast on the foam again, but we decided just to save money, not cut that out, build a thinner precast and do a flashing over the seal. Same look, it's just less work and less material. This is another example of shifting the you've got to consider what the sandwich of your wall is. The hollow frame needs to come out past the jet board to catch that thin break there. Here's an example of what we do for roll-up door. You have a wood buck, you have wood return, that way you have a nailer for that. For anything. Just more details about the same thing. And then also, like, just as you saw in the movie there last night, any architectural profiles that are outside of the building, it's just additional foam, just EFIS foam to make that architect. So up higher, our higher windows, whatever sills are made out of EFIS. You see here. And then we have our thin brick down below. So it's up to 66% more energy is used with a 2x6 wood frame wall system versus the ICF wall system. This is that case that I'm getting to here. So in a hot box, they did a hot box test. What that is, they build a box, they put a wall in between. And it just happens that one of these walls was a 2x6 wall with your 7/16 OSB plus your air barrier and your siding, and then a half-inch chipboard, just a typical residential wall. The other specimen was put in a 6-inch ICF wall with an acrylic finish on one side and then half-inch chipboard on the other side. So those are the two assemblies. And so mechanically, they tuned each side of the box, one to minus 30 degrees, 31 degrees Fahrenheit, the other one to 69.8 degrees Fahrenheit. And they kept that condition constant. So what they were determining with this hot box test is how long it was going to take for these temperatures with constant mechanical input to equalize on two sides. And this is where it gets really cool. So almost immediately, the 2x6 wall started to drop and started to equalize. And so at about the 60-hour mark, the 2x6 wall was in equilibrium. The ICF wall didn't even start to change until 50 hours in. 50 hours. Now let's think about that. How many hours are in a day? And how many cycles, temperature cycles are there in a day? Usually just one, night cycle and day cycle. So if that ICF is holding the temperature of that thermal reservoir in a 24-hour cycle, it most certainly can do it at 60. Which means that the core of that concrete is almost like the law of inertia. You know, things in motion didn't stay in motion. Well, it has inert thermal reservoir properties. It does not want to change. And the foam on each side of that concrete is going to keep it in that state of, with that unchanged state. So that's what's cool, is that it keeps you cool and it keeps you warm depending on how you mechanically tune the space. In Utah, we can have 50-degree temperature swings from day to night during the summertime and then into the fall. And so an insulated concrete form will definitely help you maintain your indoor air temperature a lot better than a 2x6 wall. So this is a letter that Foxwatch received from a cinema guy in Wisconsin. He wrote to Mike Schwab and said, Mike, I took a look at the heating costs for the Desert Star Cinema in Lake Dalton and the Star Cinema in Johnson Creek, Wisconsin. The results are very interesting. The JC Theater has a 40,000 square foot footprint, slightly smaller than that of Desert Star, which I believe is in the mid-40s, 54,000 square feet. You probably have the actual figure. Since the theaters use different utilities, I looked at therms instead of dollars. Johnson Creek used 5,938 therms. Desert Star used 3,229 therms for essentially the same time period. The heating systems are very similar. The numbers show that Desert Star used 46% less energy than did our other theater. The use of commercial block instead of CMU is a primary difference in construction. Please let me know if you have any other questions. It's pretty good at 46%.
So I point one thing out on that too. If I remember, commercial block used a steel stud, a steel connector, because commercial block's no longer in business, but we did a theater about that same time. And the connector at that time, all of them were still a galvanized sheet metal stud. And so you had some heat transmission through the concrete. So my guess is, that letter's 2001, my guess is today would be even better.
You're correct. You're correct. Polystyrene and commercial block, add steel to west,
Yeah.
to the foam panels, and they did have a little more thermal penetration.
ICF properties, because the thermal mass is a huge seller for me, as an architect, to try to let people understand what kind of cost savings they can have. But in addition to that, the ICF block, the EPS foam is closed cell. And so the concrete that you get in there, you get a higher compressive strength, even more than what the concrete was designed for, because it's fully hydrated during the curing process. Winter installation is not a problem because the concrete's insulated for blankets over the top. 9 to 10 foot lifts without blowouts, but blowouts do happen. I'll leave that. They do happen. Shorter construction schedules, high STC rating, which is good for theaters. One of the biggest things is trying to abate the sound in the low frequency range. And ICF did a great job of that. There's 5 trades in one system. You have your structure, you have your installation, you have your furring, and you have your weather resistant barrier, and your the schools that we do not use a WRB. We do a termination bar at 12 inches up above the foundation wall, and then flash down over the foundation. Inherent in a 6-inch wall is a 4-hour UL class assembly for fire rating, disaster resistance, blast, hurricane, earthquake, tornado, and also ballistic resistance. Do you guess which one's the ICF house? That's a pretty convincing photo, especially with all that's going on around it. Can't remember where that was.
That was Katrina.
That was Katrina.
No, that's Mexico Beach.
Mexico Beach, Florida, yeah.
The interesting thing also on that one is if you look behind that house, you see another roof. That's a wood frame house that the concrete home protected.
And we saw that same property up in Tahoe with the fires up there. Actually, some ICF houses acted as a break and saved the houses behind them from the fire. Yeah.
So how does in the heat of the fire, is the ICF exterior white melted away and it's really the concrete providing the fire?
Concrete's an ultimate thing, but the foam doesn't propagate flame, it's self-extinguishing.
So it'll melt in heat, but it won't actually melt.
Correct.
Sorry, question.
Yeah, go ahead.
Do you know offhand, like, that melting of, the toxicity of melting foam versus wood? Is there any comparison on what's worse?
I'm sure there's information on top of my head on that.
So, because of the closed cell foam, it's 90% air, and all the toxicity test reports on the smoke and vapor emission off the EPS printing is less than pine. You want to breathe pine smoke, you want to breathe EPS burn smoke, and we go low and get out. But it's less toxic than lithium.
Yeah, the polystyrene is expanded steam, right? So typical your X-gases, the other foams that are termed as bad or have chemicals of that nature. So it's 96% foam. So
That's great.
And the XPS foam will hold 20% more water than EPS will. So if you have that as your foundation insulation, then you're losing some of your insulation value just because of the water control.
So I know some of the ICFs are a different color insulation. Do they all use expanded polystyrene or some using like a blue board?
95%. Everybody's using 1.5 pound nominal EPS, expanded polystyrene.
Is that just because of cost, or is that because it doesn't absorb water and because?
It's a correlation, it's a marriage of the engineering behind concrete high pressure holding power, and the insulation value and cost. It also has the highest durability versus the other foams.
So it seems like someone's also added a graphite additive to the
Yeah, you
polystyrene.
can drop in graphene crystals and get a little bump in the R value. But again, we would rather speak to U value and whole building energy use analysis. R value doesn't begin to tell the story.
So this is just a little short video that Randy actually, if there's no sound, it's fine. It's just seeing what's going on is what's so nice. I don't know how many of you have kids, but fidgets are a big thing in my household. And like slime and stuff like that. I mean, my kids can watch slime videos for hours. But like, this is truly so satisfying.
Is that it, Roy?
I mean, no, come on. How cool is that? Yeah, that's cutting out your electrical boxes. That was an electrical contractor. Just run right outside that stud in the wall. And then it's shallow enough for them to do power actually nails in the back of the box right into the concrete.
So is that heat or vibration or?
It's heat. Yeah. And it's, you can set wires up. And when we cut away on the outside, if we do for block, sometimes we'll have contractors use the saws a little bit. Sometimes they'll set a depth on that and it'll just smooth right on down.
So I noticed he said he was anchoring the box to the concrete, to the back of the box, but can you also use a flange box and attach it to the stud, or does it crush the styrofoam between?
It's better if you go to the concrete. Since there is 3/4 inches of foam, it will probably compress a little bit.
Now, can you run your components, or do you have to run all your electrical in conduit?
If you want to have flexibility in the future for boxes you want to plan for the future, conduit's the way to go. But you asked about flexibility in the wall before. You just pull the chipboard off, cut a new groove up above the ceiling, and new drop, and just pass the chipboard over, and that's how you do some retrofits. And it's pretty easy and slick to do it that way.
Right, so if you know, in kind of larger projects, so if you've got 4 or 6 inch conduit that you have to work with, you're either planning that in the concrete initially, or you're looking at a styrofoam thickness that can accommodate a 6 inch conduit?
No, actually what you do is you don't think about conduits at all when you're designing the ICF.
And you're surface mounting everything?
Yes, you just throw that out. That's just the best way to go. Because you want to maintain as much of that envelope as possible. And if you're putting voids into concrete, that's no drive your structural engineer nuts in the first place. And then secondly, it's just easier to have those trays come in after the ICF's already in place.
So take advantage of the thickness of the foam as much as you can on the fur out. So you got to add some cost for furring out to accommodate those conduits.
Correct. In my opinion, that's the best way to go. There's also helical steel fibers you can add to concrete. Someone else I think is going to talk about that today. I have not done this yet. I would like to have the structural engineer do some tests or something that we can do this, because it'll be a lot less rebar in the walls. I know there's some engineers up in Canada that are doing this now for their concrete reinforcing. Also, I've heard that it comes up pump trucks. So there's pros and cons to everything in this world, right? But do the pros outweigh the cons? I don't know. I haven't used it, but it is out there. So this is our first ICF project. So I'm just talking about some of the projects we've done. This is in Demising, Colorado, at Colorado Mesa State College, is what it used to be called. Now I'm not sure what it's named to. But it's a 226-bed student housing complex, 4 stories. Western Colorado University, that's what they changed to. It got LEED silver. The reason why this became an ICF project for us and why this was our first, because the state of Colorado, for any state-funded building, had to be LEED certified. And so we're like, this might be a good opportunity to explore ICS, because we had wanted to up until this point, but we didn't have an opportunity. So we approached the university with this system. This is actually a new Dura block. It is a different color block, but it's still EPS foam. That's just a trademark. Anyway, so 4-story student housing complex. Foundation was Nudura block all the way down to the foundation. You see it's pretty green color. Big window openings because we had some span between floors. This flooring system also was a Hambro system, which is it's a steel truss with a spline curve at the top flames, and you put it down your plywood and then pour your concrete, and it turns a integral system and pull your concrete off. It's good for sound transmission between floors. We also did a cold form truss roof on this one. You can also see we did not use a WRB. All of our hard surfaces were on the ground up to a certain level, and then the rest of it was taps or each profiles. Then we did 4 replacement schools in Idaho Falls. Out of ICF, this is the hybrid system where most interior walls were CNCAs, and once we transitioned to an exterior wall with ICF. State of Idaho wrote the Idaho Falls School District its $500,000 check for energy efficiency. Because not only was this an ICF school, each of these schools had ground source heat pumps. Specifically, this is a pump and dump system where we pump water from upstream in the aquifer, garnered all the heat from it, and then dumped it downstream. So we had a constant temperature flow year round with this school. There was 4 of them. So you can see here, there's some of the interior seat unit there.
So Steve, do you think you would do that again, keep the interior as masonry, or once you got the ICF guy on site, would you just go from the ground up ICF?
I would only do it if the mason was doing the block and ICF.
Do you think it saves money to keep the block in the building?
I think it does, if the mason doesn't hit you too much with it. Because right now, the junior high school that we're doing right now, that goes out and starts construction in January, is actually going to be block on the interior, some of it. The contractor convinced the owner to go that approach to save some money. So unfortunately, like the change happened like a month before the drawings are due. So that's why I'm a little tired today because I'm still working on that, trying to get it out. But anyway, yes, I think there's some savings, but if you haven't seen a contractor build both trades, then you can do that approach. Otherwise, I wouldn't attempt it. So here's one of the hybrid walls. You can see how it transitions. All 4 of these schools were replacement schools on site, 2-story. That's finished product. We had sea view up to 10 feet, and then eaves or taps up above that. Royal Junior High School, this is a new prototype for the Weaver School District. They hired us to do this one in 2 repeats. And we approached them about doing ICFs, and it just so happens, if you've got a good client or someone who's willing to take a little leap of faith based on your own testimonial, those are hard to come by. Well, we started over with this guy because he's like, do it. Because we convinced him on the energy savings that there would be. We proposed doing also a faster schedule. We did get it delivered a year early, but it wasn't because of ICFs. And you'll see why, because you can see how many corners there are in this building. And so just to explain, so this is the main entry of the school. We have our shear walls were ICFs. Our 2-hour separation wall here was an ICF. Our cafeteria wall here, ICF. This second wall on the interior corridor was ICF. Any interior wall was ICF if it was structurally supporting something. Our gym wall, actually was on this perimeter here, was all ICF. And of course the full perimeter of the school. Second floor, this is the gym going up, the indoor running track, and then a second level on the classroom and media center. So under construction, just an aerial view. So you can see here, this is the shear wall that we installed here. On this next version, this next repeat of this, these are actually going to be CNU.
Come on, Steve.
I know you want to sell a lot, Randy, but I gotta keep these good graces with my owner too, so. So it's just, we're covering it up, so. Anyway, so we're two-story tile here. One of the challenges we had on the back side of this, and you'll see the scaffolding is set up on the inside of this instead of the outside like this. That was a challenge for us because there's power lines right here. And Mason did not want to set their scaffolding. I understand why. But we had to wait for them to get all the way to start to do steel. Just some of the challenges of construction, what it goes. Steel deck being installed. One of the things that's interesting about this school as well, right here on this little hill over here is Hill Air Force Base. And F-35 Lightnings are doing sorties every day. And so for this school, ICF was really good for sound isolation for that school. Because they're loud. So this is the gym, and this is the athletic area. Okay. So this is a rendering of what we hope it would look like at the end. You know, you do a rendering for our clients, they're like, well, this is what it's going to look like. I think we did a pretty good job. So we're CNU up to 10 feet. We have some CNU accents surrounding some windows and eaves and taps up above. Another view. Interior here, this is the student collaboration area with cafeteria, gym. This project also won ICF Builder Award, People's Choice Award, also Associated General Contractors K-12 Project of the Year, and Utah Construction and Design from Wichita State and Large K-12 project. Okay, now let's look at the school by the numbers. So we were able to obtain some billing for three junior high schools in that same district. We have Roy Junior High, which is built South Holland Junior High and Walt Coast Junior High. You can see the differences in square feet. So during these monthly billings, after 3 months, these are our totals. Roy Junior High was 3,400. Now this is just looking at gas and therms. This is just for gas. Because all three of those schools have gas heating, heating. So these are all three heating months, that's why that's important, so we have these three numbers. So this is the delta between this and these as well. Cost per square foot of heating for Roy is this. It's 46% lower than North that new junior high school, and 32% lower than an older junior high school per square foot. To me, that's significant. I'm glad to see those numbers because that wasn't really was able to approve that to the others. So.
Question about that.
Yes, please.
Sorry. How did you manage the post-occupancy training of their facilities team? And that looks like a pretty big campus and building. And usually it's the facilities team who's not treating the building with the proper things to make the thermal properties come to life and get these kind of numbers. Did you do extensive training with them, or how did you make sure you could have this data at the end?
A lot of it's in mechanical automation, and they do a pre-occupancy training with the school district and maintenance people. So the people who install the equipment do video training. They'll actually do video training so they can reference back to it, talk them through how to set all their, all their controls and whatnot. But yeah, it's just, they do the training, if that's answering your question. Not only the suppliers of the equipment, but also the mechanical engineers on the project. Because mechanical engineers, based on our envelope calculations, they're downsizing their equipment in order to meet what our envelope is in our comp checks is telling them. And so that's how they get it. I'm sorry, I'm going long.
No, that's all right.
Okay. Does that answer your question?
Yeah, on our end, once it gets to facilities, it, you know, we hardly ever see, you know, the hard work we did in design come to fruition because it falls apart in facilities and trying to manage the building, so.
Yeah, it's written into our spec to do that, so that's a requirement for commissioning. You know, it's another school we did, it's with ICF, not the overhang part. That would be hard to support with concrete, but this is just in addition to a high school, innovation high school, you can see just that small part is. We had to have a 2-hour wall separation. This is on the heels of the Royal Junior High in the same district, so we're like, well, let's just keep building blocks since it's already here, let's just keep going. So this is the finished product from that. This is in addition to an elementary school in Ogden School District, which is north of Salt Lake. ICF, and then we have standard brick on the outside, but you look at that building, you can't tell it's an ICF building. It ties into the old building really well. This is the elementary school that we're doing right now with a thin brick that's going to be done in a couple of months in Logan. Just some renderings of what we anticipate that looking like. This is a view from the street of the ICF form. All the interior walls in this one are ICFs if they're structural. Here's the back side of it with some thin brick installed, so you can see how that's turning out. Recently had the tower cap put on the top. That was a prefabricated tower cap. Our founder, when he originally designed the school in 1893, because we're rebuilding now 128 years later, he had a tower on it. And so we're trying to keep some of that history with that school. Another really cool thing about the school as well is talking about net zero. There's a canal that runs through the property this way. And it flows from like March to October, which is primarily when you need heat, but when you need cooling. So when the canal flows, we're pumping from here down to our camper and then dumping back upstream for cooling for that building and that canal. It's just an irrigation canal. So that's something to help with energy efficiency as well. This here is West Haven Junior High School. This is what we're working on now. So this is the same thing as Royal Junior High. It's just mirrored, same pig, just different color lipstick. That's an architectural phrase. Right? Anyway, so that's what we're working on now. So I just don't limit you what you can do architecturally, which I appreciate. So in conclusion, net zero ready buildings start with efficiently designed building envelopes. That's where it starts. Hard to change an envelope. You can change the chemical systems, you can add a photovoltaics. If an envelope isn't good, then you're starting at that spot. There's real value in the thermal reservoir. Keeping that reservoir maintained at temperature or having a reservoir that doesn't want to change has real value to your envelope as well. Insulated concrete forms have many benefits for all building types. I can make this available to anybody who wants it. Just some resources. Thank you. Do you have questions? Yes, please.
Question back here.
Sorry.
For subterranean use, are there any properties of the ICFs that would negate the need to use something like Zypex if you're going to put a Zypex additive?
I would say it depends on your groundwater, where that is, your geotech. Because if there's a lot of groundwater, like we do have groundwater in that elementary school we're doing, and it's not ICF to the foundation. We're doing concrete stem walls. So I would say yes, but it really depends on your geotechnical work. The presence of water, I think, has everything to do with it. And I think you can add that into your concrete mixture so that you have that in addition to your insulation barrier from the foam itself. But I wouldn't go subterranean even still without doing another layer, a sheet of waterproofing down there. As a matter of fact, that elementary school, even though we are down below, we actually we used bentonite to fully make that into a concrete plug down there because we do get spring runoff and we're below the water line in that elementary school. It makes the school district really nervous. Me too.
That's bentonite house, Steve.
We have to have
put into wall connection or?
We put it down in the aggregate before the footings were installed, wrapped it up and over and up the wall.
Oh, you're talking about the bentonite sheeting.
The sheeting, yeah. Sorry, not yeah, the sheeting. Other questions? somewhere, yes.
So I talked to you offline, and Utah's a dry enough climate that you hadn't run into this problem, but one of the things I found in researching ICFs is that because they do such a good job of kind of curing out the concrete, we've all run into problems with vapor emissions on floor slabs, and then you try and glue down an impermeable finish, and the glue fails because of the vapor continually emitting from the floor slabs. Probably in some part of the country that creates humidity problems inside the building. That concrete gradually still is releasing that vapor that's never, gotten out, and it creates potentially for mold on the back of your drywall. Does anyone run into that in human parts of the country, and how do you deal with it?
I don't know, I've only done it in the arid parts of the country, which is, I'm grateful for. Anything that you think about?
Some of your mechanical systems can help with that, air exchangers,
Heating dryers,
things like that.
One of the things that we do is we have our mechanical engineer write to their spec that they have to just start up at least 2 months before occupation. It has to run constantly until occupied, so it can dehumidify and get that moisture out of the air. Because it's such a tight envelope. Of those elementary schools now that falls, we did have some condensation issues because their maintenance staff were turning it off at night and weren't constantly running it. And so we did condensation on sills and stuff, some of our classrooms, but as soon as they got that running and dehumidified, it was fine. I haven't seen any mold problems, and obviously this isn't a food source for mold, the foam isn't.
Yeah, I think it's just the paper on the back of the drywall.
I could provide some more commentary on that later, I have some background on that, but I'll say this, the big problems are when you have temperature variations. Being wedged within the foam prevents the concrete from undergoing significant isothermal changes, which prevents moisture from driving out and driving back in. So that kind of negates that. It stays there as more or less a thermal reservoir, but not moisture constantly coming out.
So one of the reasons I'm trying to gather information, we are in such a dry climate in Utah that, in my opinion, it could be a real plus, because there's a lot more problems in Utah with people having it too dry. So if you can give them a house that has a humidifier essentially wrapping around the whole thing that helps the interior humidity, it might actually be a sales feature of using ICF.
Another thing is that the face of my furnace box block. It has undulations, it's not a flat surface, so you don't have paper sitting exactly flat on the surface. So there's an opportunity for that to escape vertically on the wall. The Fox box itself is embossed. You also have these vertical channels in between. So there's a place for the moisture to travel on the backside of that.
We need to move on.
Oh, okay.
Yeah.
Thank you. Sorry.
No, it's awesome. Thank
A lot of time. Thank you, everybody.
Thank you.
Go ahead.
Yeah, I was saying that we're going to set up the presentation. Patrick had a few things he wanted to know.
Just one thing I wanted to mention. Very common misconception, if you will, and I think some of it's just in our own expanded polystyrene is not styrofoam. It's a completely different product. This product actually, with some challenges, is recyclable. And I happen to know someone in the room that actually surfs on recycled EPS on his surfboard. So that's it. It's not styrofoam. It's expanded polystyrene. It does have recyclable qualities to it. Johnny Gonzalez goes back and forth with that all the time.
Everybody else, that's the first thing they say when they see it.
Right. Oh, that, trust me, Brandon and I and Johnny, it's like constantly, yeah. So anyway, that's all.
Yes.
Yeah. So next up, we have Mike Visser of Visser Engineering. He's been a licensed engineer for 32 years or so and has worked throughout the country. And I'll let you kind of take it from there.
Thank you. I am here to talk about multifamily projects in particular, although I am actually the engineer of record for the Synopsis project that we saw last night, so we're going to hear it from so today I'm talking about multifamily projects. I am the owner of Visser Engineering. We work in Federal Way, Washington, which is about halfway between Seattle and Tacoma. An engineer since 1985 and so forth. My office does movie theaters, multifamily mixed-use projects, self-storage projects by the dozens, modular construction all over the place, and tree houses. People put crazy amounts of money into trees. I have no explanation for it, but they do. ICFs are insulated concrete forming. We talked about that. That's the ICF. Everything else is not. Structurally, the only thing that matters is the stuff inside the ICF. This is a concrete building. The elements up here, they are not attached to the styrofoam. They are attached to the buckouts in the styrofoam. They're attached to concrete. We have a code for it, ACI 318. Code just gives us the rules of the road. Again, it's a concrete structure. The foam, you can remove it all, we don't care. Nobody else has talked about this, but when you take a wood building and make it concrete, once you make the exterior to concrete, it's no longer needs to be a type 5 building, it can be a type 3 building. The only rule for being a type 3 building is the exterior needs to be non-combustible. Once you do that, you essentially double the allowable area of the building. You add another story of free height to the building. It's not free, but you can do it. Now instead of 4/2, it can be 5/2. So there are additional benefits to using ICF beyond the insulation guide. The only rules are the exterior bearing walls need to be 2 hours. The interior bearing walls need to be 1 hour. Floor construction needs to be 1 hour. Roof construction needs to be 1 hour. All of those things you had to do already as a type 5 building, except for the 2-hour exterior bearing walls. But as a concrete wall, at 6 inches, it already was. A 6-inch concrete wall is automatically rated at least 2 hours, regardless of the mix design. The elephant in the room is that the elephant is heavy. We have a wood wall, it weighs about 8 pounds per square foot, 10, something like that. Once we fill a 6-inch void with concrete, it weighs 75. Floor weight, if it's wood, 20, 25, if we put a topping slab on it, something like that. We put concrete on metal deck, it's gonna weigh more. Our bearing walls, the loads are gonna depend on the wall space. So we have ranges for our wood walls, might go from 900 PLF to 1300 PLF. They aren't big numbers for wood, that's great. These are concrete walls with concrete deck, they're gonna weigh a lot more. We're gonna be up to maybe 2300 PLF based on a 10-foot tall wall. But the cool thing is, while we multiplied the weight by maybe 2, the strength went up by a factor of 5. Our seismic forces, they're going to go up too. They're a function of the building weight. For wood construction, our total building weight might be 40 pounds per square foot of usable area. That's going to translate to seismic forces about 6 times SDS. SDS is an acceleration value depending on your site. For all the way up to an ICF building with concrete floors, I could be talking about 21 times SDS. That's more than 3. It's about 3.5. My 6-inch concrete shear wall with minimal reinforcing in it is 10 times stronger than the strongest wood wall that I can do with plywood on dug first studs, nails 2 inches on center. I'm going to make that work. We took an example project that we've done in wood and said, okay, what would that mean? Our general approach would be demising walls, they're going to remain bearing walls, they want to be concrete. Corridor walls, probably want to be concrete. The exterior definitely wants to be concrete. In this instance, we're keeping the wood floor. And there's some issues with that, we'll talk about that in a minute. Our base connections, if we're on a post-tension slab, is not substantially worse than it was before. We have dowels coming out before we had anchor bolts coming out. We have reinforcing in the wall because we have to reinforce our concrete wall. It might have two faces if it's really highly stressed. Generally speaking, we're not going to expect to do that. At the edge of openings, we're going to have extra reinforcing. That might just be because we have an opening and a large amount of concrete. We just have to deal with the stress at that location. Or we could have boundary elements at the end of shear walls, and they could be fairly extreme if we have limited shear walls available to us. But if we're using corridor walls and demising walls and the exterior walls, we got a lot of wall. We're not going to be that high stress. Again, our attachment to from the floor to the ICF walls, we're going to have ledgers. The concrete is going to extend out to the ledgers. We're not attaching to styrofoam. Simpson does have a product, which I understand is like $15 a pop or something, that will magically move the load through there. I don't exactly know how they do it, but they've got testing, and it's okay with me. So this is a typical corridor situation. Again, whether the corridor wall needs to be concrete or not is kind of a project-specific question. In my opinion, if the cost of your ICF wall is on par with doing it as a wood framed wall, you might as well do it. You've got the sound benefits. If there are structural benefits, go for it. As a concrete wall, it needs to be anchored to your floor system. And we've got Simpson products for doing that. Floor systems that are available to us are generally, you stick with your plywood on wood joists, no problem. You're going to have fireproofing to that and probably have to deal with sound issues, but it's a sound system. It has strength limitations, and we'll get to that in a second. Concrete on metal deck supported by steel joists. I think there's a lot of reasons to like this. I'm going to jump to the next one and we'll come back to it. Concrete on metal deck, just spanning from bearing wall to bearing wall. If you make that deck a little bit thicker, you'll meet your 1 hour requirement without any extra need of a Type X chipboard underneath it or anything else. The downside is you still have to deal with sound issues. Structurally, I like this one. Generally speaking, you probably want to do concrete on joists. And then add in extra chipboard for your fire resistance and to finish out your sound resistance. The issue with a plywood floor system is that it's a flexible system. And that has consequences that your structural engineer is going to get stuck with. And then he's going to come back and he's going to gripe at you. You should just expect it. There's costs associated, a complexity cost associated with keeping a wood floor. One of the big ones is that lateral loads, the size of these loads, need to get to your shear walls. So we have what we call collector elements, and this is from ASC 7 that points to things that is identifying as collector elements. The problem here is that the loads can get really big. The code has multipliers on them. Their numbers are such that usually we assume you can't do it in wood members, period, or that you can't get the connections to work. And so by way of a comparison, 2 number 5 bars in a concrete on metal deck can drag 35,000 pounds. There's no Simpson connector that's going to do that, and the wood members that you would have to use are going to get very large very quick. So moving lateral loads around is much easier than a concrete on metal deck floor, so we tend to like that. Before we get to what that says, so summarizing where I am right now, I would say, yeah, your building gets heavier. You're going to use elements which are stronger. And if you're sitting straight on the ground, if Fox blocks can make the thing pencil, and you've got energy benefits, it's pretty straightforward. You don't have any big complexity. Structurally, it's a pretty easy project. Then, you put it over a hotel, or it's a mixed-use project, then we're talking about the big spaces. How do you handle that? And that's where it is. We've been practicing as structural engineers in the room. So, bad news is, you're not going to get to use a two-stage because the top is no longer as flexible as it was before. If you do it through a suggestion, which is exterior plus Demising Walls and border walls, you almost certainly have an irregular building as well. So you're probably going to have to do a modal analysis for this thing. And all that's a ton of work. And then it's going to give you answers you don't like. Solutions. There's some solutions, none of them are great. Once you're putting this thing up in the air, you have made it a lot more complicated. You can put transfer girders underneath your post-engine slab. The problem with this is usually that architects don't like nice straight walls like where you want them to go. Nor do they usually line up with columns, and it's just difficult. We can just make that sucker thicker. And there's a lot to that. Now, the values I have up here are really rough guidelines. But generally speaking, when our office is doing a multi-family project in this construction, we're kind of expecting that layout-wise, we're talking about 20-foot bays on the exterior, 30-foot bays on the interior, and our PP slab might be 14 inches thick. It's going to be something like that. But what ICF walls above, the building has gotten much heavier. Even if my floors remain wood. If I was starting out with 14 inches of PT slab, and I'm just going to deal with all of this crap in my PT slab, so I might go to 18 inches thick. If I put concrete floors above, which is what I want you to do, then I'm 19, maybe 20 inches thick. That's a pretty thick slab. We would prefer at least to make it somewhat higher. Not just transfer girders, because that's kind of problematic in and of itself. And not just making the whole thing freakishly thick, because that's kind of problematic in itself. If we use white shallow beams and some level of thicker slab, we can do a lot of this work. It's still a complicated structure. Your structural engineer's still going to drive me, still needs to get paid for a good chunk of work. Hotels are a little bit different than how they lay out. They're going to need open space for conference rooms, pools, those kinds of things. They're kind of non-negotiable. Our assumption is that you'll have some walls that will probably continue all the way up through, but you'll have some walls that want to go away. And you're going to need columns to carry those loads. And here's where you really get into the layout of the building. If this is the corridor, and that's the hotel room, and then every 12 feet or so, I got a wall. If there's a pool down underneath all this, then I can have columns that are here underneath my wall and not here in my corridor, then I can use those walls as deep concrete beams. I might need to make them a little thicker. And this column here, oops, let's come back to that. What I'm going to do is put a column, 2 columns, somewhere along this beam line. And these columns really want to be like 11.25 inches thick, because I want to strip off the styrofoam at least 1 level up. And I want to maintain the thickness of that column going all the way down. If I do that, then I can have that wall be both a wall for just carrying my bearing load, but also as a deep beam. This is clearly I get my cake and I take eat it too situation. Now, the architect wants to move the beam, the column over here underneath the corridor. All of that cake and eat it too is gone. We're going to put a separate structural element underneath that wall. It's going to go from here to there, and it's going to be almost certainly a very heavy wide flange. It will not be manufactured in the United States, and it will take you months and months to get. Those kinds of things want to be discussed between the developer, the architect, and the structural engineer before the column is where you don't want it to be. Because if you can put it where you want it to be, everybody on that team is going to be much happier. And those really deep. Other hotel solutions. You put a transfer girder, it's something really nasty, it looks like that, and people hate the structural engineer. Or the wall beam situation we just talked about. I was told the crews do this. So, if anything I said sounds sketchy, dubious, I made it up, or anything else, now is the time. To ask. And if there's no questions of me, I've got a few questions from you. I asked my name structural engineers, and looks like that's the structural engineering table. Did you all know each other and plan that?
So Mike, you had one slide that talked about single layer versus double layer, and I'm
Yes.
I always advise that if you can get away with single layer, it really is the preferred approach, mainly because of ease of placement.
Absolutely. So in ACI, you're allowed to take your allowable shear stress and shear wall up to 2 times the square root of FC prime, which is like 100 psi with 1 layer of steel. Once you cross that threshold, once you get to 101 psi or whatever that exact number is, then you are required to have 2 faces of reinforcement. One of the reasons I'm proposing that you want to be generous with the amount of shear wall up there is to keep those stresses down, so we're not talking about two faces of steel, so we're not talking about cord steel at 2 inches on center, or any of those kinds of things. Now that said, getting back to we had a project which really didn't look like this, but I'm going to use it anyways, in which, because of the layout of the superstructure, it was a hotel project, we really wanted the superstructure to have 6 shear walls. There was a bend in the building, actually 2 bends in the building, and a bunch of discontinuous things and whatnot. And there were these 6 locations which were really ideal. They went from like podium up to the roof. They were long enough, they did what I wanted them to do. I paid some road penalties and you pay the bill. But they were perfect. They were strong enough, they kept it rotating. We just loved it. The problem was they stopped at the podium. And with just 6 shear walls, the loads get pretty freaking big. And The owner was insistent from day one that we were not continuing to strip walls down. The whole system was going to change. The walls, they were going to move. And we completed our design of the superstructure, those 6 walls, and we get to the podium. And then we had the $1 million meeting, which is when we kind of come to Jesus and talk about your 6 shear walls. And the developer had his contractor there, and I described the situation. We can terminate these walls. We can make that podium strong enough. But our estimation was that the thickened portion of the slab that was underneath 2 of the walls, which was over a large meeting area, was probably going to push 4 feet thick. Might not have been 4 feet, might have been 42 inches, but it was certainly not going to be 24. If you've ever designed mass concrete, the problem with mass concrete is it has massive amounts of reinforcing. Even if it's just minimum amounts of reinforcing, it's a lot. So he described the whole situation to the guy's contractor, and he's punching numbers and doing what he does, because I don't know what the costs are, he does, it's his costs. He goes back, yeah, that's like $1 million. So, Mr. Developer, it's your $1 million. I don't care. It's not my hotel. I'll do what you want. Our 6 shear walls went to the ground because it was $1 million. It was his $1 million. So, having those conversations about the difficult parts, they want to happen. I'm going to strongly suggest that if you're a developer and architect and you think you don't need your engineer until you got all that other things figured out, and you're talking about doing an ICF on a podium, you need to get your engineer engaged like now. Because smart decisions will save you a lot. Bad decisions either are going to result in a change in the architecture when you're already way down the road, or a lot of money out of the developer's pocket. I like the structural engineers, you're nodding. All right, my guys give me a thumbs up. So. Questions, complaints? And just before you complain, whatever you're going to do, man.
I want to know how to convert that, get rid of that 5/1. What's the parting wisdom for the folks in this room? That's our nemesis right there. Right? Seriously.
Okay, well,
that's our nemesis.
I would say, first off, that wants to be a type 3 building.
Yeah.
This is an urban environment. There's nothing zoning-wise that keeps that building from being that tall. It wants to be a type 3 building. So I get another floor.
Mm-hmm.
It's another floor of less expensive structure. So that's an easy choice to make. You don't do anything else, you just make it a type 3 building. Despite the complexities, if you plan reasonably in your layout of the below podium and the above podium so that your structure can come through without being too painful, then ICF can make a lot of sense from a structural point of view. But you need to understand for your structural engineer, there is a big difference between sitting on the ground and sitting 24 feet up in the air. Mm-hmm. Huge difference. We can deal with it, we can help you, but you've got to let us in the room to do it.
Is the engineer the person that we should be focusing on to flip that? Or is it, I mean, obviously the owner has some say in it, but who is on the design team, who do we work with to get that so it's all concrete? Is it
I
you,
would say that would be a developer and architect conversation first.
Okay.
I mean, Patrick told it, it's a developer architect conversation. I mean,
Okay.
you know that, we've done stuff.
Yeah, exactly.
Similar.
You're doing one right now, right?
And it's all wood, and it should be ICF.
Yeah.
Both of those guys kind of go right into the CN for that discussion to cost them too.
Yeah, I mean, we're going to get the call after that decision has been made.
Okay.
And it will generally be at that point, are you going to let us talk about how we make that work and be less painful, or are you going to give us a plan and 3 months from now we're going to have that $1 million meeting?
Right. Right.
We can do it either way. I mean, I don't care. I get told all the time things which are delusional, and that's the direction we go until you get to reality.
I would just add, like, from an owner's perspective, a lot of times, you know, we get this analysis of it's this cost or this cost, but it's, you know, sometimes it's too fine of a lens. When we're looking at, you know, from a larger project perspective, it's an easier conversation and a better informed conversation for the owner if you're saying, is this and this one-to-one, but also you've got this that is going to help you or save you down the road. And usually when you're just having one conversation that's just structural engineer, you're missing maybe some of those other elements.
Oh, certainly.
So it's always good to for us to understand more of the implications than just the problem that we're trying to solve at that moment. Because there's usually some other benefit that we're just not aware of to make the most informed decisions.
Oh, absolutely. And again, the structural perspective is very, very narrow. And frankly, a lot of it comes down to what's worse for me. I mean, I don't know where this is built. I can't see it from my house. It's not my problem. I didn't spend money on it. What are the heating bills? I don't know. My range of experience and knowledge here is very limited. But I can really help, or I can clean up on aisle 5. And you know, frequently I get no choice. And the worst case is, again, the $1 million conversation, where at least I'm giving you the choice. I may not have, you know, we had a long-standing relationship with the developer, so I knew that I could go into this meeting and have a positive discussion. He was going to have his money guy there. It was going to be okay. Frequently, that's not the case. Sometimes, I have no idea who the developer is. I've never seen the guy. I mean, I'm just a guy who gets a check. He doesn't give a shit about me.
That's why we love the party meeting at the beginning.
Absolutely.
Everybody's there.
Absolutely. Which is why strong communication through the design team is so important, because everybody has these different perspectives, and no one person can necessarily see the whole picture. Architects are generally better, but it's usually the developer who's got the best feel of how all of those things come together. I'm just trying to help you get past those things.
Let's give Mike a hand.
Later that I'm an idiot. I'm just going to provide a small bit of evidence. So yesterday, I was driving around town with my wife, and we stopped somewhere for lunch, and we're walking back to Starbucks, and I see the sign in my eyes that's not nearly as great as it was, so the letters are small on me, and I start at the wrong end, so what is that word? Chinooka? What? Happy Chinooka. I turn over. What's Happy Chinooka? Happy Hanukkah.
That was awesome. Thanks, Mike.
And my time killer story is about the time I convinced my nephew that he could take pills and turn into a dog. It's a much longer story.
So next up, we got Robert Yates here with Roy Structural Engineering. So, Structural Materials Engineering. He's a fiber expert. Not to really butcher his intro here, but he's a special engineer for fiber reinforced concrete slabs and structures. And since 2019, when we started his own consultancy, he's been serving a diverse group of clients, including precast, ready-mix producers, specialty labs, fiber manufacturers, concrete contractors, and general contractors from his home office. He's been in the industry for about 16 years, working largely in California, but he's also licensed within 39 different states throughout the country. So brings a lot of experience specifically nowadays to fiber reinforced concrete.
Thank you very much.
Thank you, and I will be brief. So I did bring a few samples of fibers in case any of you guys want to just come up and sort through them. We have synthetic fibers, these are called microfibers. In the bag, actually, there's some smaller ones called microfibers. And then I have, I got two different sets of plastic fibers, and then we have the Helix that Steve, that you mentioned earlier. It's popular in ICF, as well as foundations and other applications, very small steel fiber. And then we have some more traditional, like hooked steel fibers that are, been around since the 70s. This is Cranber Harris from, I think, Germany, and then there's Beckert from Belgium. They also get into like ultra high performance little teeny fibers that you can put in high dosages. So anyway, these are here for your perusal. And so I just wanted to introduce fiber reinforced concrete and just talk about converting from rebar to fiber. Really that simple. Fiber's great, but when you try to use it in like high seismic areas, you can start to run into code roadblocks. So if you didn't take anything away from the meeting, know that you can do most things with fiber, but not everything without special testing. So just to be realistic with the crowd. And that's something I actually want to talk to NRMCA about. Maybe we can pre-qualify some ICF thicknesses, heights, things like that with different fibers. Because that, I think, could go a long way to helping engineers just be able to quickly pull things off the shelf and get rid of some of the reinforcement. So we have macrosynthetic fibers. These are like discrete, maybe 1 to 2 inch, 2.5 inch fibers that you can mix into concrete. And instead of having to place rebar, you just mix your reinforcement right into the concrete at the ready mix batch plant. You could also put it into the concrete truck on site. It's just less popular to do it that way. It's easier to control quality at the batch plant. If you're worried you're not going to get your right fiber in the truck, just send a special inspector to the batch plant to do special inspection. And then you can go from continuous to periodic. Lots of different types, lots of different patents, different ways of establishing bond in the concrete. And so some of you may have been familiar with some of these. I know Fortifero bottom middle is pretty popular. It's a nice finishing fiber for slabs on ground. Usually tough strands that are like top middle. The BASF fiber, I think, is the bottom right, or that might be the Strux 9040 from Grace. So there's lots of different fibers, lots of different companies. These are steel fibers. Your typical hooked end, top left. These are a couple inches long. Very strong steel. They get their bond because they kind of have a little hook, just like rebar has deformations. And then top right is kind of Beckert's innovation. They have 2 hooks. So you have a little bit more pull-out resistance, so you can use a higher strength steel. So you start playing with these 2 things and try to balance out a good solution. You have crimp fibers, and then you have the helix, which is like a cool special shape, and then they twist it to help again with the bond. So it's all about like fiber. It's all about pull-out. You're trying to pull a paper clip out of concrete. How can you get it to stick? So the fibers all have different properties. I just wanted to point out I don't know if this that does work. So when I'm comparing, like synthetic to the tape, the kind of flat plastic fiber, it has a lot of surface area, but it's not super, super strong. We have more of the round fibers, that are more like sticks. They're more rigid, and they have embossments to grab onto the concrete. And they have like a little bit more, obviously not as much surface area as the tape. But when you start looking at kind of all the steel ones, one thing I noticed when I first learned about helix is how low the dosages were. It'll be like 9 or 12 pounds per cubic yard of steel fiber. And typically I'm like thinking 50 or 60. Like, how in the world are you guys doing this? And so I had to look into it just so I could responsibly recommend the fiber to customers and stuff. And it really has to do with they have a lot of surface area per fiber, but it's notice it's kind of almost the same perimeter of fiber grabbing onto the concrete, but you have not as much area, so they're able to get a special shape that has a lot of perimeter but not a lot of material, right? So you have more fibers, less money. So not to get too into the math, but I just wanted to let you know if you see helix dosages and no way is that possible. I think it probably is pretty accurate, and just based on some of these numbers I was crunching, because I was like, that's crazy, you can never do that. But I think this is how they do it. It's about 3 times more efficient in terms of bond. So for what that's worth. So if you have a project with ICF and you're looking, I'll do a Beckert or I'll do a helix, just expect pretty different dosages, and don't just throw one away or keep the other. They're providing you kind of the same engineering, even though they seem wildly different. The thing about the helix, it's very short, so it won't do well for big crack widths. So if you're expecting a large crack width, or you're doing like big deformations on a seismic element or something, better to keep the helites more like slab on ground stuff, things with multiple cracks or smaller crack widths. If you're doing like ground support, shotcrete ground support for a mine, big huge crack widths, then obviously like a longer fiber is going to do better. So that's just kind of a quick numbers thing on the differences of fiber properties. They matter, and it's hard to compare synthetic and steel because the different specific gravities, so you can't just be dosage. You have to really look into it and look at like volume percent. So just a quick conversion, if we're going to go like ICF wall, 6 inches thick. This is a residential ICF. And we'll just convert minimum reinforcement into fiber, and that way you just kind of see the process real quick. So number 4 bars is 18 inches, and that's a reinforcement ratio of about 18% down here. So we have like from the code some minimum, vertical bars and transverse bars requirement, and we're going to convert from those into fiber. Again, sort of you're seeing it's about 0.2%, 0.18%. These are kind of like standard numbers of minimum reinforcement for concrete. So the whole thing is you got to compare apples to apples. So you just have to take your rebar and spread it across a certain area to get that reinforcement ratio, or that 0.18% kind of a number. So this is the math behind it, because a lot of times people get caught up on number 4s at 12 or number 3s at 18, but really you should just be talking about this, the reinforcement ratio, because that normalizes it, so you can talk apples and apples. So in this example, this is how we actually calculate, number 4 at 18 is 0.185, so we're like, hey, we need this from the code. So that's what we're going to use. And so I get a set of plans, I'm like, oh, let's see if we can do fiber. So I go in and I break a beam and bending with a whole bunch of fiber in it. And this is the stress diagram of the beam I'm breaking and bending. And at the bottom I get some big, 300 PSI or 500 PSI of like tensile strength that the fiber gives me. But I got to convert to axial strength, because remember, if I'm having rebar is like good intention, but I have to calculate like the reinforcement ratio is a tension number. I have to take that and say like, well, how much fiber do I need like in this bending test? Because we can't test fiber in tension yet. There's not enough standard. So we have to like test it in flexures. So there's this like whole divide by 3 thing. So if I need like 100 PSI of tensile strength from my reinforcement ratio, I need 3 times that in flexure. And then I know how much I need to put into my beams in the lab and test it. So it's like actually not exactly 3, it's somewhere between like 3 and maybe 0.4 is the conversion from tension to flexure. So here are the results of this little ICF example. If we were doing just strength and temperature reinforcement for like a floor or something else, we would divide the rebar by 2, because of the early age properties of fiber. It kind of reduces the need for rebar in the first place. But in a structural application, we actually care about actual strength. So we're going right from rebar to like PSI axial tension. Here's that conversion factor from like pulling to like bending, 0.37. So we actually need 300 PSI from our lab test. And then we include some statistics about variability of the material. So, we need 330, and all that comes out to like for synthetic, we need somewhere between 9 and 13 pounds per cubic yard of fiber. And for steel, we need kind of around 50 pounds per cubic yard of fiber. But again, it's like, I can't compare these. So really the way to like talk about fiber is more volume percent. I need 0.6% fiber. And just as a reference, like if I wanted fiber to act like rebar, I would need about 0.2%, or I would need 2% fiber. And that way, like concrete would stretch and it wouldn't crack in one place. So anything under 1% fiber is kind of like there's going to be a single crack somewhere. Anything above 2% fiber, it's going to crack everywhere. It'll stretch just like rebar stretches. So concrete can start acting like rebar as a material if you put enough fiber in. It's kind of cool. So these are all kind of the answers. Depending if I were designing a beam, then it would be even like a higher amount, just because the variability is such a small element. The fiber is more variable, so I need to have more insurance against a low result. So there can be a little bit of difference between like a large element like a wall and like a little element like a beam over a kindergarten. Like what if a few fibers didn't get in the right place? That's a huge problem. So that's captured in this like statistical number here. And then down here it's kind of like, oh, if we use helix, it's, instead of, being 0.4%, it's 0.14. And you're like, oh, how does that work? Like how do they get away with three times less fiber? And I was struggling with that. I'm like, oh, I can't recommend this stuff. And then doing those specific surface calculations, I'm like, well, I guess it's 3 times more surface area. That's how I'm doing it. So those are the answers for the conversion. And so I guess, yeah, the takeaway from this is, we're going to use 18 pounds per cubic yard of helix, or about, 50 something pounds of Becker steel fiber. And so those are your numbers for replacing minimum, reinforcement, and that works horizontal and vertical. That's not, you don't have to like double that for both. It's like that one dosage takes care of your verts and your pores. And so that's the number you would use to kind of budget the concrete. One thing to know is that if you're using, like, especially for higher seismic zones, or if you want to do fiber only for like a tilt-up wall or an ICF wall, the code really wants the wall to have about the same stiffness after it cracks. So if the thing cracks like in wind, it's like being bent in wind, it really doesn't want the wall to have like a lot less stiffness or strength after a crack develops. So you need to have enough fiber to have this kind of response, where instead of like one crack opening and all of a sudden your strength drops, you have a crack forms, and then you actually have like a gain of strength as the wall starts bending. That way it stops bending. You don't want like sort of like runaway deflection, right? Because then that'll lead to a collapse. So if your wall starts bending, you want it to start pushing back even harder the more it gets bent. So flexural hardening response. So that's kind of a key term when you're going from rebar to fiber. You really want, for structural applications, that fiber needs to be flexural hardening. And so that you're up in that kind of 50, 60 pounds per cubic yard for steel fiber range, or maybe 15 pounds per cubic yard if you're doing that for synthetic fiber, which you could use for flexural hardening stuff. So this is kind of a full diagram that you've taken out to explain all by itself, but there's just lots of different properties you can get out of concrete, just depending how much fiber you put in it. So I can do anything with fiber. So Becker has a code approval. One of the challenges is the building code. Fiber isn't written into the building code very well. It's only really in there for minimum shear reinforcement, like for beams and something. So if you wanted to use it for like a mat slab for an ASRS facility or for like a high-cube warehouse, you're like, oh, I can't use fiber, it's not in the building code. Well, a couple companies have, taken the initiative and gotten agency approvals, which you can do to work your, new innovative products into the building code, like a Simpson moment frame or a epoxy anchor or whatever. So these are like kind of, if you want to do a two-way mat slab, you have to have a FSH, so flexural, hardening. If I want to use fiber in a horizontal diaphragm, like Mike was talking about, then it needs to be tension strain hardening, so that's like 100 pounds or 150 pounds of fiber, that kind of thing. So it's just, the whole game is all about like how many pounds per cubic yard and how much is that going to cost, and then how much labor you're going to save on rebar. And you kind of have to just work it out. So you can do anything you want with fiber. It's just really a matter of, can you mix it into the concrete? Can you get the right consolidation properties? And can you pay for it? Let's see, there's lots of guides available. Again, a little bit light on the building code side of things, but plenty of design support from ACI. And then, like if I'm doing a structural design, and like if I have to do it for seismic, or I have to do it for crack width control, or some sort of more sophisticated design, I actually use the European concrete code because it has really well developed design rules for fiber. So this is what we're looking for in the American Concrete Institute, which is what the building code uses. So in the future, this is really what we want fiber to be like. So I can reach out to fiber and use it with rebar or by itself as a structural material. Right now, you have to work a little harder to use it as a structural material, right? You have to use like an agency approval, and the building code official's like, oh, is this appropriate? And if you're going to use it in like a seismic design category D, E, or F, it's going to end up being a harder process, because you're going to have to probably have a peer review on your design with fiber. You have to have an engineer who really knows how to use fiber. So it'll slow things down a little bit. So that's why we want to eventually get to where we can design with it. But they have used it in like seismic applications to reduce the congestion around like link beams and all the confinement steel for columns and things like that. And so there's a lot of testing that supports the use of fiber to reduce the congestion of the reinforcement. And really the best solutions are the hybrids, where you have some rebar and then fiber's helping reduce all the other stuff that makes it impossible to consolidate concrete, right? So there's some projects in Washington that have used that, but again, it's like a peer review firm had to come in, the building department had to like be okay with it. And so it's always hard at the beginning. So some of the stuff I talked about today, you'll see in the future, so we're just preparing you for it. But you're like, hey, if we could get the fiber in there, that'd be great. Well, the answer is you can for like the lower seismic design categories, or for gravity loads and things like that. Like, it's great, it's perfect. We can get rid of like all the rebar, we can get rid of part of the rebar. But for the higher seismic design categories, it's a challenge. We're doing nonlinear analysis, we're doing finite element analysis, we're having a peer review firm, that kind of thing. So it'd be great if we could work with some sort of industry group to like create some sort of catalog of like standards, or like standard like ICF wall thicknesses and aspect ratios or something that could just kind of get things going, so that not every project turns into a research project. So I think 17 minutes, sorry, 17 minutes. So I don't know, if you have any more questions, let me know. I know we're a little short on time, but I'm happy to answer any questions about synthetic or steel and fiber reinforced concrete, analysis, use, mixing, finishing, whatever you want. So thank you.
Great job, Ron.
My pleasure.
So we have one more, a little bit on paving, and then lunch. Lunch is actually here.
It's Brian Killingsworth. I work for the National Ready-Mix Concrete Association. And we've been talking vertical stuff. Let's talk horizontal a little bit. Every building should have some form of parking associated with it, whether it's a parking garage or whether it's a parking lot. And when you're paving your parking lots, you essentially have two options. One, an asphalt option, two, a cement-based option. I guess you could do, I guess you could do granular if you wanted, but I don't think your clients or your consumers would like that very much. But we have a brand similar to what you see with Build with Strength on the building side. We have a brand called Pave Ahead with a mission statement that means a lot to us. To others, maybe not so much, but really it's about safety, resilience, long-term value, all of those types of things that we talk about on the building side. It's the same type of thing that we look for on the paving side as well, when we're talking about our parking lots. We have social media channels, we have online tools, we do design assistance. So the same type of assistance that you can get on the building side, you can get that on the paving side too. And you can get free information if you have questions. I too also have a team of folks dispersed out across the country. Your California and your kind of Pacific Northwest representatives. One is John Hansen and the other is Don Clem. So if you need their assistance, you can talk with anybody at NRMCA and get their information, or I'll show you a website that you can go to. So we have this Pave Ahead website. Lots of really good information on there about designs. There's free education. There's information about contractor partnering between the producer and the contractor in terms of getting these parking lots built. And we have other tools that's available to you. So again, paveahead.com, go there, find all that you need on paving. And this is what I'm talking about. So if you've got, this is an ICF building, You've got great concrete parking all the way around it. Really, concrete is a great option for paving. Now, what's the one thing, when you think about concrete paving, cement-based paving, what's the one thing that always comes to mind? What is the one negative that people will always say?
Cost.
I heard cracking, that's one. We can take care of that.
Joints.
Joints to cost, I heard cost, right? Somebody said cost. Cost generally is what people talk about. It's too expensive, you can't do it. Asphalt's much cheaper. And I would agree with that statement with a caveat. Typically, when we're designing our asphalt parking lots, we're under-designing for traffic and soils. When we're designing our concrete lots, typically we're over-designing. So we don't really have a good apples-to-apples cost comparison. What we tend to have is an over-designed, too expensive concrete, under-designed, relatively inexpensive asphalt. So when you design them appropriately, the same, then we can be very cost effective and we can be very cost competitive. Okay? But there's more than just conventional concrete. So there's a lot of other cement-based types of ready-mix materials that you can use, right? Conventional concrete, obviously, is a great option and what you're going to see probably 95% of the time. But there's others. We've got pervious concrete. Anybody have any experience with pervious concrete? Okay. Roller compacted concrete. We'll talk about that in a second. And then we can do other things. We can actually put a concrete overlay on top of an existing pavement, an existing asphalt or an existing concrete pavement. We can actually put a layer of concrete on it and use it just like you would see an asphalt overlay. We can do the same thing with concrete. But then we can also do full depth reclamation. That is where we essentially take the existing pavement that's there, grind it up, add some cement to it, cure it, grade it, do all that stuff, and then we can put a surface right on top of that. Okay, so we have a lot of cement-based options available to you. This is the one that we typically see the most, right? This is conventional concrete. What's the one thing you don't see? What do you not see? You'll see forms, that's one. Somebody see any steel in there?
No.
There's no steel. Everybody tends to think concrete paving needs steel. You got to have steel. You don't. Okay? Generally, what do we see? Where do we see the steel? We see welded wire mesh. Where is it? It's right on the ground. It's not even shared. I can take a bunch of $100 bills and put it out on the ground, and it does effectively the same thing. Okay? So if you are going to put steel in it, make sure it's put in the right spot. That's typically in the upper third of the paving. But we don't really need it. How do we not need it? Joints. We put our joints in the right places and at the right distance. Okay? If you walk onto a concrete parking lot that doesn't have any steel in it, and you're using 30-foot joint spacings, what are you going to get?
Cracks.
Cracks. Now, if I took that same unreinforced and put those at 12 to 15-foot joint spacings, you won't see those cracks. Okay, so appropriate joint spacing is one of the things that you can do to correctly detailing it. It's one of those things you can do to improve performance. This is a boom screed. One way that we can very efficiently and effectively pave is using boom screeds. We're talking about efficiency. We have some contractors that are doing warehouse paving. They're doing 100,000 square feet in a day. Okay, so they're doing massive amounts of paving in a single day. Now, is that typical? No, it's not really typical. But these boom screeds are great for commercial paving. Like I said, very cost competitive. We can help meet sustainability goals. When we're talking about the different materials that we can use, Portland limestone cement as part of our paving. There's a lot of things that we can do to make our concrete sustainable. Plus, if you're utilizing pervious concrete, that can also benefit you from a sustainability standpoint as well.
One thing that a lot of people don't recognize is the reduced need for lighting. Concrete very reflective, so we can reduce the number of lights that we need. Sometimes we can save up to about 30 to 20, 25 to 30% cost potentially. There's less lighting that's needed. Efficient paving rates, and then also the biggest really is reduced maintenance. We have many lots across the U.S. that have been in place for 30, 40 years and have basically done zero maintenance. So significant reduced maintenance cost. Like I said, reinforcing steel, not necessarily required. Many times we don't even have to place a base material. If we have a good foundational material, subgrade material, we don't even have to place a base. We just engineer that soil, put the concrete right on top of it. And then we need to make sure that we're designing for our thickness for the traffic and the soil conditions that we have. Great options for heavy-duty pavements. We see it in warehousing all the time, but also great for trailer storage, for employee parking, that type of thing. So we've got conventional concrete. We can use roller compacted concrete, concrete overlays, pervious concrete, and even lightweight aggregate types of concrete where we have internal curing going on. We can use all of those different types of materials in our surface. Then we can utilize, when we do need bases, we can utilize cement stabilized materials, or we can do that full depth reclamation and put a new paving surface right on top. Or we can use lean concrete. We can also, when we have poor soils, we can stabilize those soils and utilize cement stabilized subgrades as a base or a sub-base underneath our concrete. Now, what are some of the innovations that we have? We can do what we call short and long slab designs. So you think about short slab designs, we're talking about 4x4 or 6x6 slabs. When we do that, we are reducing the amount of stress that's on each slab, so we can reduce thickness. The other thing, we can do long slab designs. Think about jointless type designs that you would see on interior buildings. We can do the same types of things. We can have 150-foot joint spacings on exterior paving as well. We can use fiber in our mixtures. We can use property-enhancing admixtures. We can integrate color into our parking structures. So there's a lot of different things that we can do. When we do need enhanced load transfer across joints, we can utilize conventional steel round dowels, but there's also different types of dowels, plate dowels, hollow dowels, or epoxy-coated dowels when we're in severe environments. So there's a lot of different things that we can do innovatively in our paving as well, and then also with our new boom type laser guided or GPS guided screeds, we can pave very efficiently. So let's talk very quickly about some of the material options. Roller compacted concrete, what is it? Well, it is a zero slump material that we are basically placing and compacting like we would an asphalt concrete material. Okay? The materials are exactly the same. It's well-graded aggregates, cementitious materials, and water, but it's just in different mixture proportions. And we use the paver, an asphalt paver, and vibratory rollers to compact it. And after we cure it, we have very, very similar properties to conventional concrete. That's what it looks like right there. It looks really, really dry. That type of material has very little, or has more sand, less water, and we place it in a dump truck. So we mix it and place it in a dump truck and then dump straight into an asphalt paver. How do we mix it? We can use conventional ready mix plants to do it. But if we're not using a central mix plant, then sometimes we've got to put in a little local mixer. As you can imagine, with higher fines, lower water, intensity of mixing is a little bit higher, right? So we need to make sure that we get it well mixed. So when we have a typical ready mix plant, it doesn't work quite as well unless you have a good mixer. What we tend to see is continuous lower plug mill mixers used to mix the materials. This is one at the Port of Houston. I'll show a quick video on this one. So this is a demo out of the Port of Houston. The Port of Houston has acres and acres and acres of roller compacted concrete, but they use a pug mill. So bring all the materials straight on site, mix, dump into the back of a dump truck, and they'll take it to the paver. Now there's two different types of pavers in paving, in asphalt paving. There's a conventional density or a typical density type paver or a high density paver. This is a high density paver, and all that means is the screed on the back puts a lot of energy into compacting that mat behind it. You can see, placed it. Now we're going to roller compact it. That's the paper right there. You can see them walking on it. You're not seeing footprints or anything like that, so it's very well compacted. So they placed this, and then a couple hours later they came in and started driving their trucks on it, just to demonstrate that it can be paved and that you can put traffic on it fairly quickly. It's not something I would recommend to do, but if you're in a situation where you need to have traffic going over into a driveway or something, you can drive right on the top of it. So that was done almost 10 years ago at Port of Houston. So this is what it looks like with a conventional paver. You see, that looks very, very different than what we saw in the video with that high-density paver. But this is just a local crew, a city crew in Indiana, that's paving some unpaved roads. And they do it all in roller compacted concrete. So this is great for these types of county roads, but also smaller parking lots. Roller compacted concrete would work very well. That's what a high-density paper looks like when we've got high-density screed. You see a very big difference in what the mat looks like. So that's roller compacted concrete. Let's talk pervious real quick. Pervious is the same thing. It's concrete. It just doesn't have any fines in it. Or it has very little fines in it. And so what that does, it allows water to flow through it because we're not filling the voids with that fine material. We have open voids. So we're allowing water to flow through this material. So the cross-section generally looks like this, typically 6 to 8 or sometimes 10 inches of that pervious concrete. An open graded base, so this would be typically like a 57 stone, something like that, clean stone, sitting on top of a filter fabric on top of a soil. This is a granular soil right here, so we get good percolation of water. So as water flows through, we get good percolation that gets down to the water table. So where can you use pervious? Streets, roads, parking lots, alleys, sidewalks, paths. It's going to be used all over. The idea is this. When we get water, we want that water to be able to flow through the structure and get down to the water table. As it's flowing through that structure, it's taking out suspended solids, it's taking out nutrients, it's taking out metals, so we're getting clean water essentially when it hits the water table. So it's a great, what we would consider sustainable type of product, and it can be used in a lot of different instances. All right, very quickly we talk about some of those rehabilitation options, the overlays, and the hold-up reclamation. So we see this a lot, poor performing asphalt pavements. What can we do with that? One of the things that we can do is put a concrete overlay right on top. This is a golf course in Colorado. We've done many, many golf courses in Colorado using overlays. But this was an asphalt parking area that they wanted to upgrade. And so we did a concrete overlay of this particular site. What do? A couple of things. First, if you want to do spot repairs, or if you need to, you can mill off portions of the existing asphalt. So you deal with the asphalt, either doing some localized repairs, or you can mill off portions of it. Clean it, put your concrete on top, texture it, cure it, and joint it. So we're doing a regular paving project from step 3 to 6, concrete paving project. The only thing we're doing here is just prepping this a little bit differently. This is a demo project that the state of Maryland did. You can see they came through, they milled off an area, cleaned it. They've got a boom screed back here. So they're coming in and dropping the concrete, putting the overlay right on top of that area that they milled out. All right, that was their first pass. Came through, did saw cutting. And then what they're going to do is they're going to do another lane right here. And they're going to pave that a little bit differently. Instead of using the boom screed, they're going to use a little truss pull screed. Okay, so they're going to come through and do the same type of thing. There you go, they milled. So they took 2 passes of the milling machine, same kind of thing, cleaned it up, bring in the concrete. There's the concrete. Bring in the concrete, and they're just doing a little pull along truss screed there. That may be a roller screed, actually. That's a roller screed. Okay. They did those 2 things all within a span of a day. The last one, full depth reclamation. So what are we doing here? So we've got an existing asphalt pavement. It's in poor condition. If it's in really poor condition, we don't want to put a concrete overlay right on top. We want to do something else first. What's that something else? Pulverize all of this material. If you have grade issues and you can't raise your top of pavement grade, take some of it out, stabilize it, and then put a new surface right on top. What does that look like? Looks like this. So existing old pavement coming through and milling. Or, yeah, they were kind of milling up. Yeah. Now, what they're using here, one thing you can do is you can use powdered cement. Don't really recommend that, particularly if you're in an area like this. You don't want dust flying everywhere. So here, they're just using a slurried cement. You can see they're just dropping the appropriate amount of slurried cement. That's what it looks like. Stays in place typically. Come through, blend, compact, grade, put some water on to cure. The great thing about this is it doesn't really disrupt. If you're doing a big street, you can still drive on it as it's curing. So it doesn't really disrupt traffic flow a lot. I mean, obviously it will some, but not a lot. And then you can pave right on the top of it. You can put a chip seal on top, you can put asphalt, or you can put concrete right on top. So you have all of those options available to you when you use full depth reclamation. So all of these materials that I've been talking about, all of the options that you have, again, you can go to pavehead.com, tons and tons of resources there. Again, we can help you evaluate your paving. We can do designs for you. There's a lot of options that you have available to you in terms of our assistance, and we'd be glad to help you. All right, so that's it for me. Questions, comments, anything? In the back, Tom?
Thank you, Brian. I'm Tom Tietz with the California Nevada Cement Association. And Brian showed a lot of projects from other parts of the country. But I wanted to emphasize that we've got engineers here in California too, doing the same sort of thing as Brian's doing, great collaboration. Yeah. But over and over again, we are surprising people with how cost competitive concrete pavements can be, as well as full depth reclamation. That's almost always cheaper. And I think the problem is people don't know how to optimize, or they just don't understand the options that are available. So I encourage you to contact us, especially if you think you want to try something different, because it won't be painful.
Yeah, we are definitely here to help. Tom has just an incredible team that we work with all the time. And we're glad to get you what you need. I saw some other questions. Hold on, Scott. One more.
So heavy concrete existing pavement that the top is shot on. Have you got something that you can do a topping that'll take like cap track abuse? Or do you just need to rip out the full depth and replace it?
Well, I wouldn't say you necessarily have to rip out. You know, there's a lot of different things you can do. You know, what you tend to see more DOTs do are crack and seat or rubbleizing, then putting something right on top. That something can be typically an asphalt overlay, or you can potentially put a concrete overlay on top of it. I have seen milling done and filling, backfilling with concrete. You can potentially have issues with that bond, so that can be troublesome. Those are difficult ones when you have, if you're talking really thick, I don't know what you're talking about, but 12 yeah. Typically cracking and seating is probably your best option there. But we can talk more if you've got a specific project. Scott, you had a question?
No, I just wanted to see if you could comment a little on, you talked about cost competitiveness, but you look at the initial cost and then the whole life cycle cost of the project.
Yeah, so when I was talking about cost competitive, I was talking about initial cost. So we can generally get in the same ballpark initially, but that point I was making about significant maintenance reductions, when you look at over the life cycle, the amount of work that you would have to do to maintain an asphalt lot versus a concrete lot, you're going to be doing a lot more maintenance and rehab, and those costs over the life really do tend to add up. So if you're an owner that owns and keeps and maintains, concrete makes a big difference in terms of the overall life cycle cost that you have. So it can be competitive up front, very competitive when you look at life cycle.
Brian, I have a question.
Yes.
So you and Tom were just mentioning the program that you put together, your design assistance report. What's the cost involved with that? How do I go about that?
Absolutely free. Go to the Pave Ahead website and you can submit through our design center. You can call CNCA. There are engineers there. We'll do the same exact thing. And again, we work very closely. If somebody calls me or calls my team and it's a project in California or Nevada, we pick up the phone, we talk with Tom and his team. So that's free. Jointing plans also are something that we can help with as well. If you're a contractor or your contractor needs help in laying those joint spacings out appropriately, we can do those as well. And those that's free as well. So glad to do that and support y'all any way we can.
Yeah, once you get your geotechnical report, send it off, and even if it wasn't available, there's a lot of options available. So I think right now we're going to go ahead and let you guys come up here and start grabbing some food. And once we all get situated, Randy will come in and entertain you through that. As he always does.
Thanks, Brian. That was great. Thank you. Of the day, and if anything, I want to really appreciate and thank everybody for bearing with us as we ran behind today just a little bit. And the most important part of the day that I am interrupting right now, I actually remember what's in the conversation, but I've been tasked with delivering a little bit of ICF information, so hopefully we can get that done. And after I'm done, I promise there will be no more folks up here that connection. So I get to represent the Insulated Concrete Form Manufacturers Association. We actually have an association. How awesome is that? And some of the members are those outfits with really good competition amongst it. And when you have good competition, you have stable pricing. So it's kind of like gas station pricing, right? ICF's per square foot, everybody's competing with each other. So there's a lot of pressure on price, and it's very stable. Members, when I first started 22 years ago, we had, there was like 30 plus brands of ICFs. Everybody thought, we're going to be rich, right? But no. The awareness and penetration of the ICF specifications in the market were really slow.
I mean, it's taken, but if you'd have told me 22 years ago that I'd be doing today what I'm doing, I would have never believed it. Millions of years. The ICFs, you know, we're in the codes, ACI acceptance, so with the evaluation service reports, all the major brands have code approval reports, so we're, in the early days, it was like the lead scouts getting shot full of arrows every time we got a building specified in ICFs. It was a lot of fun. So anyway, in a nutshell, we're concrete and little foam on each side. Everybody gets that, right? I love our structural engineers. They can care less about the foam. But on the architectural side, yeah, you got to care about the foam because it's going to stay in place. You got to put the finishes to the face of it. So, you know, that's what producers will work. But the most beautiful thing I heard today was integrated design approach. Okay? Where you have structural, you have design, you have GC builders, everybody's at the table looking at the builders and the projects and working together out of the gate. That's absolutely the most beautiful thing I've heard today. So what is an ICF? Well, it's a foam, couple of foam panels, and you've got these cross ties. And pretty much everybody today has a high density polypropylene cross tie. Interesting to note, these cross ties 100% post-consumer recycled. So we're trying to get plastic out of the waste stream, create a market for it, and putting it into building material. Pass that around. So that plastic cross tie, that has a threefold purpose. First thing it does, it shares a horizontal rebar, and you can see the rebar fingers. So it gives our structural engineers different spots, not only in the concrete wall to specify where they want the horizontal bar. Second thing it does is it holds the head pressure of the concrete for it. Pull that apart. Oliver, pull it apart. Come on, man. Yeah, there we go. Oliver, you need good attention. So the concrete head pressure holding power on ICFs have just done nothing but get better and better and increase over time. And the latest generation products have a ton of head pressure holding power. And the third thing that thing does is it becomes a furring stud. So you've got a furring stud. In this product, you've got it every 8 inches. Okay? And I actually dropped a couple of screws in there. So $1,000 to anybody that can pull that out. Pass that around. Go ahead, pass that. I'm just kidding. You don't have to pass that around. And what that looks like under construction is pretty simple in all of our manufacturing plants. We've got these recycled polypropylene beads that come to us, and then we put them through a injection machine, and we make those webs. And we make those webs, and then the webs get palletized, and they get delivered to our 18 manufacturing plants across the country, and those webs then get hung into the molds. Now these molds, these tools, they are an EPS foam manufacturing plant, and the mold doors close, and these tools that produce these shapes, they have just thousands of steam vents. So if you look up close to these blocks, you'll see little circles like little shower heads. That's actually a vent where steam and high pressure is introduced. And it takes this closed cell foam and it solidifies it. It fuses it all together. And then out pops a brand new, fresh, and warm insulated concrete foam. Okay? So these machines that we have, and our competitors, all of us, we produce currently on a 24-hour cycle due to demand. And each one of those machines, that thing right there is about 1.2 mil. So we have, and the molds that go in it to produce the various shapes, quarter box, 45, straight box, etc., various core sizes. They all run 40, 50, 60 grand. And we've got 20 SKUs, 18 plants. You start doing the math. The infrastructure is really in place today. And I couldn't say that when I started. So what you're basically looking at is 4, 6, 8, 10, and 12-inch concrete walls. That's the range that's nominal. So 80% of all the ICF business is in the 6 and 8 inch concrete floor. That'll get you all residential, light commercial, multi-story, typical. 10 and 12 inch boards, ready retaining wall grade, going up tall, 20 stories, 10 and 12 inch to do a job of FEMA storm shelters and whatnot. And recently we've introduced 14, 16, 18, 20, up to 30 inch widths with the compact product line that has webs that can lock together and bring us out. So doing stuff like gray beams on military bases, 30 inches wide. Doing another theater here in California where it's IMAX walls that are going up 60-foot clear span with an 18-inch ICF concrete core. Okay, so it's not a big part of the business. The big part of the business is the 16-inch concrete core. We get this sugar plastic. It's called Styrofoam, and we blow it up in a popcorn machine, and that's this white foam part. So that white foam part is expanded polystyrene. We expand it, and it comes to us in those totes. You see that picture in the upper right? And we expand it and turn it into expanded. And then the expanded gets automatically funneled into those molds, and we fuse it all together. Interesting fact, one of those totes is about 4.5, 5 foot square. It'll make an entire truckload of product. So it's a very efficient use of a base material. And we always want to point out the last bullet item. We're taking this low density material, and we're wrapping it for buildings, continuous installation for the lifetime of the building. As soon as you start doing some analysis on that, the energy performance and carbon footprint, et cetera, is pretty amazing. So what do? Western United States is my territory, everything west of the Mississippi. I run around primarily American Airlines, National Rental Car, and Hilton Hotel. That's my home. And then I support this stuff through design, through value engineering support, through education, development training, comparison. And again, if you told me today this is what I was going to be doing 20 years ago, yeah. I was absolutely not. If you told me 20 years ago. So, examples in public works, City of Las Vegas. Sam Tolman's the head architect over there. They've done nothing but LEED silver and LEED certified public works buildings, fire stations, police facilities, and they started plugging in ICF quite a while ago, 10 years or so. So we've done 4 fire stations, another one coming, a museum, police facilities, so municipalities. Like the City of Las Vegas. Same thing with the City of Phoenix, got the fire stations. I love template buildings that get built over and over. That's a county sheriff substation. It's in Texas, of course, which everything's bigger in Texas. And so we got the first one done, and they did another one, and the first one took 4 weeks to stack in 4 hours. The second one took 3 weeks. Right? So if you build the same thing over and over again, it gets better. Here's a Phoenix 911 service center that's 50 feet tall. That one required some columns every 20 feet, so we had a 10-inch core, ICF wall and a shell, and then about every 20 feet there was a bump out from the interior on a column that was mandated by our structural engineering friend. I'm going to show just a couple of quick pictures of devotional stuff, and the reason I want to do that is we're going to take a walk. We're going to get to go see this really neat multi-story, but we're going to go take another little adventure walk, and we're going to see a really nice, remarkable devotional project. This one, however, is not the one we're going to see. This is like 28, 29, 30 in the Phoenix market, and the Diocese of Arizona has embraced ICF, and they just keep building these churches over and over. And I like them because, sales. But some of the unique aspects of these are, arch tops on the windows, and so I get asked, how do you make an arched window? Well, I hand them a sawzall. Right? We're just formal. Just look at this like plywood, essentially. You know, it's just ready to be plywood. You're gonna cut plywood on an arch and buck it out, same thing here. Cable tips and whatnot. So the job we're gonna see here in a few, it got designed and it had a lot of non-45 degree junctions. And nibbling masonry is really becoming expert with ICF installs. They devised, you see this right here? Those plywood sheets? You see that hinge on that piano back there? That's just 2 plywood sheets with that hinge screwed to them. And it's not fixed, they can bend it any way they wanted. It was so cool. They would go right, so they would miter the formwork, the straight wire, miter it, butt them together, and they would take that piano hinge with 2 plates and they would just screw it to each side on the ICF stud. And it held it in place. Great for the floor, and they could reuse those interior, exterior, that angle over there, that angle over there. It just worked out really cool. So we're proud of that for sure. And that's it going up. So most of the ICF brands, we make 90s, we make 45s, okay? But all of these are off angles that were just simply mitered and held together with that plywood configuration. And the scaffolding and the bucking were done right alongside that, and each pour height was between 10 and 12 foot. So that's what that looks like, and I'm really excited to walk over there and show that to them. We're going to submit this church in 2022 for an ICF Builder Award, and we're really proud of the ICF Builder Award. All right, I'm going to burn through some of this federal military stuff. Anybody doing federal military in here? You guys, from time to time, that's right. So we are actively involved and engaged in global shipments of insulated concrete forms for our federal military applications. I've got projects going on at Camp Lejeune in the Carolinas. I've got projects going on in Nellis at Edwards Air Force Base, and too numerous to list globally. And part of the reason is ballistics resistance, blast resistance, anti-terror force protection requirements. What are we? Cast in place concrete, right? And so all the testing that's been done in Quantico on ICFs is last. The combination of the muffling effect of the foam, it's kind of like a little bit of a shock absorber with the increased compressive strength of concrete that secures within the foam cavity, hydration better. You get some really exceptional blast results with concrete. So here's the thing. ICFs, this has been known as an exotic, expensive animal for so many years, right? I go in and try to talk to people, and then you get to roll their eyes, oh, it's so expensive. These days, I'm getting conversions from steel stud with internal installation, whatever kind, bat, and then continuous rigid. That wall assembly is getting very close to the cost of what you can do ICFs for. And so we're seeing more and more like these light retail. I mean, a Dollar Tree store. Come on. that's a box, right? And it's the cheapest box you can possibly build. And a Dollar Tree store in El Paso, right? We're on our 3rd one in anybody from El Paso? I don't mean to denigrate El Paso.
Yeah. My best clients from El Paso.
Okay, all right. Gotcha.
Do a lot of concrete parking.
Okay. Banks, we get the bolts in the banks too. You do the ICFT off the exterior walls, put a concrete lid on it, the vault door, bam, bolt, right? So, 5 building dominion springs, school after school after school. Texas is remarkable. You know, you can fly in a DFW, and within a 60-mile circle of the airport, there's over 200 full ICF schools. And a Texas grade school rivals a California high school in size and scope. It's just bonkers how big these projects are. So for a lot of years, the #1 state in the nation for ICF schools, Kentucky. But then Texas grabbed it and took a hold of it. And then we're seeing, like today in Missouri, the first ICF school is bidding, okay? Just a few years ago, the Neil Armstrong, the man on the moon, the first man on the moon in the state of Utah with an ICF school is sitting over here, right? And so markets break open and it start to happen, but we had to put a plant in Texas just to get the volume needed for the schools. So each school will take anywhere from 30 to 80 truckloads. And if you think about a half a dozen schools going at the same time, you start to see the needed volume that's required to supply the market. And so raw materials and whatnot need to go. So this is a cool video. It's got great music to it. The narrator is wonderful, but I don't have any sound for you. So we're just here to submit it, but we are really proud of this one. And Stephen, thank you for it. It's truly a remarkable build. This, by the way, you can just access any YouTube. Just go on YouTube, Lloyd, in your eye, and it'll pop up as an ICF photo award. Theaters, you already know about theaters. And do you know why Randy loves theaters so much? I hate windows. Stop putting windows in these buildings. All right? It's my volume. They're eliminating. So it is a really cool. So this is what these little black dots and little black squares. That's actually our logo stickers on that. So disregard. The big thing to realize with theaters though is that you've got these long runs of straight wall and they're really tall, and we just ship truckload and truckload. So that's the most important thing. The other thing is that because of the STC rating on the ICF wall assembly is, and especially with the low frequency, the bass, these new sound systems, last night you heard it, right? You heard it from the theater next door. They didn't have the demising walls. 90% of the theater auditoriums and the shells that we do the demising walls out of the ICF because of the THX sound systems and checks. We can eliminate that low bass penetration, auditorium to auditorium. So not only do I get the outside, I get the demising walls, and those are again tall, straight, and there's no windows in the demising. Particularly here today, we would love to talk about multi-story, multi-family, and the reason being is that's where the lowest hanging fruit versus our competitor, the wood. Softwood lumber, right? So we're targeting that as an association and as a group to go after. And this is Lubbock. I'm about as enamored of Lubbock as I am of El Paso. I have never been there when the wind wasn't blowing. And this is Texas Tech, so they've got half a dozen dorm buildings like this. They're all 4- and 5-story, massive campus, just unbelievably big. So that's quarter walls, and that's also a temporary bracing that goes to the ICF every 6 foot and allows that installer to plumb through the walls. Okay? So this is all it's hollow core precast floors. So those hollow core precast floors, that's the top of the ICF floor. They're going to bear on 4 to 5 inches of the concrete, then you get a topping slab and block it all in, and repeat as necessary, kind of like shampoo. That's it. Pictures taken from the hospital next door. This is luxury condos. This is the building. You're going to see them as soon as I can get you over there. Here's our hospitality footprint. So what's going on with the hospitality guys? So same thing with the theater guys, same thing with the churches, same thing with the schools. It's just an owner that's looking at 3, 5, 7-year life cycle assessment analysis, operational costs. Basically, in a nutshell, ka-ching, what's going to make me more money? What type of building can I build that's going to be more profitable for me, for the duration? None of these guys really care about green or sustainability. I've talked to them. They don't. They really don't. So what we find is on the hospitality side, because all the PTAC units in every room, you put up an insulated concrete shell and you get PTAC units that are not running 24 hours a day. They run only a little bit because of Mr. lack of inertia. That's what's happening. So we are seeing, well, COVID put the brakes on a little bit, but right now we're at over 300 hotels across the country. Okay, and we're not doing much to even advertise it or talk about it. It's just the operators, the owners are talking to each other. Here's a guy in the Phoenix market. So this is HD Management. They've got two 4-story stick frame Hampton Inns in the greater Phoenix area. They pay about $8,000 a month on utility bill on average across the year. So that's electric. That's electric, and that's all the air conditioners every day running, day in and day out on those 4-story stick frame ones. And he did an energy use analysis. He did comparative costing. So 4 years ago, he went with an ICF, and instead of 4-story stick, what could he do? He could go 5 stories with ICF. Right, Mike? Yeah. Okay, Mike's in agreement. Jesus, Mike agrees with it. So he ran this one for 2 years now, and when I come to town, he takes me golfing, which is awesome because this one, it's his highest profitable hotel across all this. It's 5-story, whole other room of keys, and it's costing him $4,800, $4,900, $4,700 on his electrical bill. Okay, whole other floor. Okay, $8,000, $48,000. That's the swing. So he just got done with another Hampton Inn in Queen Creek, same thing. So he's not going back, and that's what we find. Hotel developers in particular, when they get one up and running and the profitability, the ROI starts coming in. RevPAR is something I learned about. Revenue per annualized room. That's their language, right? It just makes them more money. That's his testimonial letter. He had figured out a 7-year payback, and thereafter more profitable building. It was more like 4 years. So, and at that time that he built it, it was pre-stick frame prices going ka-ching, right? All right, so enough about hotels. I'll blow through the rest of this. That is a great slide, though. And I'm going to load this thing up on Dropbox so anybody that wants to can grab it, and away we go. So on the Concrete Design Center, highly recommend you guys reach out to our buddies that are great hosts and the Build with Strength guys, Patrick, Brandon, Chris. These guys are just monsters. So a lot of times when I'm talking to a developer, I say, hey, let's do this. We'll do a comparative costing stick frame to the ICF. Stick frame with floors to ICF walls, concrete floors. And these guys will come in and provide a design assistance. What is it?
It's a design assistance program, but we also change it to design assistance proposal, so the DAP works, or DOC design assistance from that.
And what's cool is line item on line item, to a total stick frame here, ICF there, and what's mind-boggling, in the last year, I have actually seen the ICF and concrete structures lower cost than the stick frame. That's remarkable. So it's all in cost, all in cost. And this is what one of those looks like. These are not our numbers, this is just local numbers on materials and labor and what it's costing for that type of building. Stick frame to that wall section and overall cost. Love that. Jacked out here. All right, so ICF versus stick frame conversions. These are actual studies, and let me blow one up for you. And the revenues for the owner. And this is where the numbers really matter. If we're trying to sell something that's perceived as more expensive, but we're selling it on the long term, right? It's the long goal. It's like, give us 3 years, give us 5 years, give us 7 years, and then it's going to be a more profitable building for you. Versus going to somebody and say, hey, we've got a way to put up a building that's going to be more profitable right out of the gate, and we can do it faster for a little less floor space. What do you think? Are we hitting on all cylinders? Yes. And so these numbers are significant. Net operating income. They don't care about me. They don't care about my desire just to ship truckload after truckload of this stuff. They don't care about concrete. They don't care about wood. They don't really care about any of it. But what they do care about is NOI. And we can give that to them, right? And we can give a safer building, more sustainable building. They don't care about that. We can give them more, all of these other things that are important to the world. So insurance cost reductions is something we don't hear enough about. But, you put up a stick frame building, and the builder strength guys, they've got this great PDF cut sheet. I think it's called America on Fire. And it's one multifamily job after another, just, fire trucks and big, huge bonfires of stick. And that's what the insurance company is. Under construction term insurance with this, remarkably lower than stick frame. All right, long history of performance with ICFs. This is where I started, in between here and here. So if I got a basement, I'd be like calling the newspaper and say, hey, we got this basement out of this thing and stuff, right? So subsequently, it just kept going up and up, and the reason being, cast in place concrete walls and remarkable attributes. So 4-hour fire rating is typical across all brands, 6-inch core and above. Okay. The 4-inch core is typical 3-hour fire rating. And you've got this resiliency. So ballistics resistance, blast resistance, wind, storm, tornado damage resistance. We are at, through Tornado Alley in Arkansas, Oklahoma, Missouri, Texas. We are at over 200 FEMA rated gym additions, classroom additions. So all these schools, and it's all 10 and 12 inch ICF specified through the structural engineer, and we'll beat you to death with that. Acoustically, remarkable. There's just something magical about sound that hits the foam and it kind of gets buffered, and then you've got the solid mass, then you've got another layer of foam. So STC ratings are great. So STC, sound transmission class, that's the speech octave range. That's all it's testing. There's this whole other octave range below that this really shines with. The energy efficiency piece, you've been hammered to death with that. But that's a neat graph on percentage of savings, traditional stick versus ICF. And what happens is this, in a really temperate climate, say where I live, Aliso Viejo, California, it's kind of San Clemente Lagoon Beach area, about an hour north. It's really temperate. I mean, we might get 60s to 80s, typically. So not as good performance, right, versus stick frame. You might get 20%, 15% savings with an ICF. As soon as you go to Granby, Colorado, say, where you've got these elevations, high desert plateaus, where you've got a 40-degree night and a 90-degree day, or you've got these really tough summer times, hundreds, and you've got these really cold. As soon as the climate goes from temperate to moderate and then up into severe, the more severe the climate is, the higher the effective R value of this becomes. We see 60-70% savings in the most severe climates. Typical is 40 to 50% savings in most climates that aren't temperate. Okay, and Steve with Design West, he did such an awesome job. And we would like to show off the 2x because you can have a 2x with R20 something insulation in it, but it's still a zip. I mean, thermal transference through the studs, et cetera, et cetera. Anyway, you've been beat up with that. With beautiful engineering, with integrated design approach, with design team integration with structural and with the installing subcontractors and the GC, you can develop a project that is very friendly for speed and streamlining with the ICF. Typical man-hour labor rates, national average across the country per square foot of ICF wall installed complete, 0.09. 0.09 man-hours. I've been doing this 20 years, and that's a great number. Okay? Take the gross square feet of ICF walls on a building, multiply it by 0.09, and that'll get you kind of the man-hours to put up and pour and clean up on the ICF scope. The theater job over at Sinopolis, by the way, James Bond is dead. That was horrible. That was 0.05 man-hours on that one. If you got a really cut up braided arches, cantilevers, all kinds of gymnastics, columns, thanks, Mike. So if you got all that, you're going to see man-hour rates, in the 0.12 range. But those are solid numbers. So we know what the speed is, and because when we put up this and we're pouring it, we're also delivering all the burring. We're delivering the air moisture vapor barrier. We're delivering all the continuous insulation. So we're knocking out those other trades. Be gone. Be gone, other trades. So that's what drives our markets. And again, these are some of the skylines. This is Eastern Seaboard, and all of those buildings are ICF. So we're getting these ink spots. Okay, we are getting in. Like the school market in Dallas, like the church market in the central Phoenix corridor. I mean, we're starting to see some amazing things. So some of the things to recognize as a designer, coursing height, this one's 16 inches. Most of the ICFs are 16 inches. There's some at 12 inches. There's some at 18 inches. There's one at 24. So you got to get kind of a little dialed in with the coursing height of your product, right? Lego blocks for big kids, but it goes together like that with the horizontal bar. So you got to kind of recognize the coursing height, because that will help with, hey, if you've got some flexibility, plate heights, top plate heights, wall heights, put it at a 16-inch increment. All right? Window elevations, sill and head. If you've got the flexibility, put those at a 16-inch increment so the guys can just course right around and tinker to it. Right? Wall lengths doesn't really matter all that much. It's this stuff cuts with a folding pruning saw, hand saw. It's it gets set at the corners and typically built to a point and then cut the length. So ICF coursing again. Wall heights, coursing increments, wall heights at half coursing. So on this one, you can see this line in the middle? That's the halfway line. There is no top or bottom. You can't screw it up. If you take this piece and you go to the wall and you snap it in, there's no way to put it in upside down. Okay? And if our designer went at an 8-inch increment, that's cool too, because we can take this, run it through a folding table saw on one face and then the other face, and that'll give us, instead of 4 feet of 16-inch, it'll give us 8 feet of 8-inch. And we'll just put those two on the top. So it makes sense too to go at a 16 or 8-inch increment. And away you go. I already mentioned the wall layout. You start at the corners, and length on walls, whatever. Make a building fit to your dimensions. It's all good. It doesn't matter. It's much better to worry about that. If you have the flexibility to do wall lengths at a 4-inch, 8-inch, 12-inch, all that, and you want to try it and make it fit into a modularized, that's great, but not necessary, because this is built for speed irregardless. On the rebar side, the most critical thing, again, please give us horizontal rebar at 16 on center. Please, oh please, oh please. Stay away from 12-inch unless you're working with a 12-inch product. Quadlock is a competitor. They have a 12-inch tall brand, so you want their rebar at 12-inch. Nudura, our biggest competitor, really good competition. Theirs is 18-inch. So with Nudura, you want to plug in 18-inch on the center horizontal rebar. So the number one critical thing on the rebar side is horizontal rebar, because this goes, a course goes down, horizontal bar goes in the top, course, horizontal bar, course, horizontal, da-da-da-da. Vertical bar will actually come in later. The other thing you want to see is the dowels coming up out of the footing or slab. We absolutely want to see the dowels coming up to not conflict with our cross ties in the product. So the way these projects start is one of the guys, he'll grab a corner block. We always start at a corner. and he's gonna walk over to the building, and he's gonna put the corner block down over these dowels. So it's wonderful to actually have the schematic and the corner block and to locate those dowels coming up out of the footing or slab, so that it's easy just to put the thing over it. And then these cross ties that are in the block, they're 8 inches on center, most are, across all the grids. So it's good if your dowels are an 8 or 16 on center, you go like that. Most of the time we see, in high seismic zones, like 2 number 7s at 6 inches on center. It's just, it's, and we make it work. But if it's possible, right, to recognize your on-center spacing, that would be cool. And the coursing of the product, so it starts at one end and it goes to a jam, corner to jam. And the first course goes down, and we utilize something called these HV clips. Where are they at? That's a school project, and they're actually getting the second course down. But these things are handy. These are called HV clips, and they do a couple of things. They'll do the horizontal part, they'll do the horizontal coursing together. And what that looks like is this right here. That locks those into place on the horizontal. So now that thing is locked together like that. And then they'll keep going down with the next course. And just like you see the guys on the video, they'll start putting the horizontal bar in, and the horizontal bar will go back and forth. So, yes, that feels good. That's awesome. So the horizontal corner bar will get dropped in, and then we're going to take the next corner and we're going to put it on here. And you've got a choice. You can go like this. You can do that. But that would be so dumb. so very dumb. Because we've got this product that's reversible. The corner has no top or bottom or left or right. You can just do this. Oh my God, that's so much smarter. Now you've got this magical thing. It's called running bond. And you can take these same clips, and instead of going horizontal with them, you can now go vertical because the cross ties are at 8 inches on center, every which way. So not only can you lock the butt ends together, you can lock this vertically with compression down to the course below. Now look at this. This used to be easier. I don't. Okay. Hey Steve, grab that one. Let's put this one on. And now, when you're running away from the corner and you're going down, oh, that feels good. Locking these into place. All right, Steve, grab that end over there. Now, instead of this modular Lego blocks thing, because of the interlock, because of the compression of the clips, this all becomes a one-piece unit, right? Becomes a one-piece unit, which just greatly assists on the head pressure holding power and the stiffness of the wall as you're bracing it with the alignment scaffold system. So we've talked a bunch about bucks. What you haven't seen is alignment system. So just like the engineering on the block gets better over time, so have the alignment systems that true the wall, keep them straight, keep the formwork straight, keep it plumb, and allow guys to make minor adjustments on the face because of that turnbuckle. This turnbuckle that's within the diagonal gives them the ability to push or pull on the wall. And these days, frankly, when I started, the results were wonky. Really wonky. If you wanted plumb walls, if you wanted straight walls, you wouldn't want to form them with foam, right? In the early days. But today, if you want plumb straight walls, form them with foam. It works beautifully all the time. And here's the recommended mix designs, and here's what it looks like in concrete placement. So typically with this brand, you're looking for a 6 to 7 inch slump. You need a gradated mix design. We love a ½ inch minus. We love a mid-range water reducer. We love fly ash content. Everything and anything. Make it greasy. Okay? Let it flow. We don't mind the head pressure. We love the ease of placement and consolidation. That's what we love. The reason being is we want concrete pours that are gonna almost self-consolidate. In other words, we're after concrete walls that don't have any honeycombing or voids, rock pockets, et cetera, et cetera, et cetera. Even if we didn't stain it, we're gonna follow ACI cast in place, we're gonna stain it, okay? Every lift, everything gets vibrated, and we just virtually guarantee and ensure solid, beautiful cast in place concrete walls with the head pressure holding power, with the right mix design and the placement techniques. You're going to get extremely beautiful results. That's a 12-inch core, that's a 7 to 8-inch slump, it's a pea gravel mix design, it's got flash and mid-range in it. The water cement ratio you want, the strength that you want, it's all in there. But it's placement ease and consolidation is what we're after. Here's a study by DSA Commission, the first ICF school in California. And schools in California, shoot me, just shoot me dead, in the face. Division of State Architect, yes sir.
Where was the school? Where was the school located?
In California?
Yeah.
The first one was Los Paseos Elementary School, Morgan Hill, California.
That's my hometown.
Oh, fantastic. So if you go over to Los Paseos, the big multi-purpose in the gym building, that's the report on this. So DSA commissioned a third-party structural engineer. So they went out and they cored ICF walls, they laid them flat, they cut them, they diced them, they looked for rebar embedment, everything they could. They did 28-day compression tests on the cores, and the head of this, Dynamic Consultants, they called me up and goes, "Oh my God, Randy, you would not believe what this cracked at." And I said, "What?" "Well, it's 4,000 PSI mud. The cylinders we took off the truck, they all popped at 48, 4,900. The cylinders that we got out of the wall, adjusted, they came out at 6,800 average." And so if you want to if you want to use ready-mix concrete for something, put it inside a foam form. The curing is just phenomenal. And that's something we're real proud of. That the only other person that I've heard allude to that is Steve so far.
So question then, there's room for improvement there on the mix design. We are at 6,500, we could definitely be much more sustainable, right? I mean, you only need like 3.
To convince a structural engineer that the concrete cures better in this and have them give you a 3,000 PSI mud instead of 4,000 is next to impossible.
Sustainable.
You know, so it's CYA, cover your ass. These guys
Yeah.
are liable for that, you know, and all the testing, all that, that's just, we've got all these test reports on cores that come out, and all of these testimonials on, concrete core guys that have to come in and cut holes in walls. They hate it. Burns up blades faster just because the concrete's so much harder.
So they could specify 100-day strength and it's in 28-day, right?
28-day, yeah.
But you could specify 100-day strength.
Oh, yes.
So again, the same thing with any shame.
That's a great
little more
approach.
sustainable.
So, yeah, give us 4,000 in 100 days instead of 4,000 in. I'm seeing some eyes roll over here. So integrated design approach. That's certainly what we've been talking to. So one of you saw the electrical and the plumbing. We chased it into the foam. Essentially, we get these concrete wall supports. This foam doesn't mean anything. It's just fluff. It's insulation. Okay, it's rigid and it's way tougher than you think. You can put sheetrock over this, and you can take a bat in it. You're going to dent the sheetrock and break the bat. Okay, so it is remarkable that way. But you also have to, after you get the utilities in, conduit, just chase it in the foam. You got to cover it up, and you need to do something called sheetrock, gyp board. That's the typical interior finish. And so you got your sheetrock guy out on the job, and you got to take him to the job and grab something sharp, like a knife, poke it in the foam, and tell him sternly, no. No. Okay? And then take that same sharp thing and find one of these logo studs. Tell him yes. hopefully. You know? So and then pull a tape measure, go from the center of one of these, skip one, and go to the next one, and it'll read 16 inches on the money. Okay? So 16 inch on center screw schedule. Instead of 1.25 inches, you're going in with 1 3/4. Coarse threaded screws, drywall all day long, right to it. Interesting to note, for our fire rating, all the testing is with 1/2 inch sheetrock good board. You don't necessarily need 5/8 type X. Cost saving opportunity there. The other thing to note, you can take full sheets and go right to the face of the wall. Doesn't matter where the butt ends land. You got studs 8 inches on center. It's a fully packed wall. So you don't need to try to cut sheetrock on a stud and then do that thing like you do with stick framing. All right, exterior finish, designer's choice. Put what you want on it. All of these and more have gone right to, so essentially treated like a masonry or tilt-up building that's got flooring on it and rigid insulation. Go right to it. You can go right to the concrete. You can go right to the studs with all manner of stuff. Ooh, here's a slide. This is scary. Take the linear feet of wall of your building, multiply it by the height of the wall, get the gross square feet, and that will get you a overall square footage. And then multiply that by 22 bucks, 20 bucks, 24 bucks. That's the bid rate range on most subs in my markets to install complete ICF. We know what the prices are. Okay? We know what the prices are. I see them every week. This is the competitive bid rate range. We get some that are down in 6-inch concrete core, and you can see easier jobs that will be in the high teens. Military work, federal work, so inspected, bureaucracy, school work in California, 10 and 12-inch cores, double curtains, all this, and you're going to see mid-20s and above, right? But most of it, 90% of it's landed in the low 20s across the country. And I'm talking about commercial, institutional, federal, military. I haven't been dealing with residential for a lot of years. How does that stack up? Sorry to my NRMCA brothers and Build with Strength, but I do have to take a shot at CMU. Okay? So CMU, you stack CMU, and anytime you stack a CMU wall up and you fur that thing out and you put some insulation to it, and then you put some rigid insulation on the finish on the exterior face because you don't like the way CMU looks, and then you sheetrock the interior face, that overall wall assembly is slower. It doesn't perform as well as the ICF, and it's more costly on the tune of $2, $3, $4 a square foot. This side by side right here, this is what's, I get to go to Costa Rica next week for 2 weeks. That is why. Really. That's where my bread and butter comes from. Anytime I see a set of plans, CMU, furred out, insulated, and finishes on the exterior face, I just giggle. Because I can go in there and I can wipe everybody out, essentially. It's low-hanging fruit. So who are the guys that are going to be bidding? In just this little market area around here, all of those guys competitively bid, experience. We couldn't say this 10 years ago. We didn't have the horses. Right now, we've got a bunch of horses that can run with the ICF. And I mentioned man-hour labor rates, 0.09 man-hours a square foot. The big part of the reason for our advantage is the lightweight nature of this product. One of the bundles of the ICF is 64 square feet of wall, and that 64 square feet of wall weighs roughly 84 pounds. So, like you're seeing up here, here's a guy, he's going to finish out the top of this building. There's one guy up there. They just petty-boned up him a bundle of block. That's 64 square feet of wall. And away he goes. Right? So really proud of that. All right, on the tail end, last few slides are just on energy demand reduction. We do have to downsize air handling equipment 25-30% to meet the exact needs of the building. You can't put the same tonnage in because it'll just cycle. Click, click, not good for it. So you got to downsize the tonnage. So these are the things that Steve's already talking about. And one of the little known aspects is that you've got concrete into the soil, so the concrete footings and the concrete going up the wall, that soil temperature, Mother Earth is also stabilizing the temperature of the concrete, and that's wicking up the walls. And that's a further added thermal mass of inertia. I'm going to use inertia. So there's the downside on that end. And the most heavily studied KBTU square foot buildings are schools, because they have to report and deliver that on their operational costs. So it's real easy to go back to schools and see what they're doing. And national average KBTU square foot, 73 on public schools. Award-winning ICF schools, net zero. That one right there is 18 square foot. But I love these. So this is a chart on a school district and their older schools versus their newer ICF schools and how that relates to teacher salaries. I love that. Love those charts. So you want to spend money throwing it at the utility company, great. Build like you've always been building. You want to use that money for something better like supplies or programs or teachers if you're a school. Build it with over 5 inches of continuous insulation surrounding a thermal mass reservoir. That's just it in a nutshell. This was my favorite story. Here's a school district. This is all of their schools. KBTU square foot. It's all ranging in a 0.5 to 0.085 per square foot. And then they built an ICF school. And they started measuring it. And they scratched their head, what the heck? So they went out and they checked the meters. No, this can't be right. And they went out again. They had the utility company out to check the meters. No, everything's right. This is their first ICF school. And thereafter, ICF schools. And so much so, ASHRAE, anybody with ASHRAE? Good. Those guys are so dry, they are not friendly. They have no sense of humor. They really don't. It's remarkable. I tried to jest with them, and They did a study. They put out this booklet, and it's the 50% towards net zero school design booklet. And when it came out, they had inquired and done research and started measurements and all this stuff, and they pretty well swatted us every time we tried to offer anything. But when we got to chapter 5, we opened the booklet to chapter 5, building envelope, this is what they showed. And I was like, oh, concrete in the middle, foam on each side. Okay? So if you go to ASHRAE and you ask them, on a building envelope, hey, what's the best way to get to at least 50% towards net zero right off the bat? That's what you're going to see. A concrete in the middle and a foam on each side. And that is that from me. That is Dakota Smith. She's my granddaughter. She used to be my very favorite granddaughter, and then I had another one, and now they're kind of tied. But she approved of this message, and I practiced this on her, and she was like, "Oh, Grandpa, that's interesting." So, okay, you've been beaten to death. Questions for me? Comments? Patrick?
How long does it take to empty a truck?
How long does it take to empty a ready-mix load into insulated concrete form walls? Give me some parameters. Straight runs wall, 8-inch thick.
Straight run, 8-inch.
8-inch, 20 minutes. Yeah. Some of the more practiced, experienced guys, instead of a 4-foot lift, going like this, they'll be doing 5 or 6 foot lifts and just going like this. So those guys do 15 minutes. 10 and 12-inch cores, you can see 15 minutes. Most of the scheduling on ready-mix loads, we just did a church in Visalia, the first height walls, another Catholic Diocese project. That was all 8-inch core. It was a double boom pump bore at 300 yards. The loads were scheduled every 15 minutes. So they split them between the two. Great question. Haven't had that one in a while.
What was about the Texas area that got them excited about ICF?
Oh, I think it was Huckabee Architects. So if you look up Huckabee, and I've got one of my competitors in Madura, there's a guy in the Texas market right now, Cameron Ware. He's really good. And Cameron started promoting ICFs and at Huckabee Architects, you know, nationally recognized firm, educational sector. Huckabee Architects did a study, and they've got it available online, CMU versus ICF. And they did an internal, in-depth study on behalf of their clients, and overwhelmingly, they started to push. So Huckabee Architects, they have, 20 school districts that are continuous customers. And they were the initial driver, and then it was trying to keep up with the Joneses. Other architecture firms are losing work to Huckabee because Huckabee's offering this, better school. And so it just kind of went boom. Kind of went boom. Yes, sir.
Question for you. So you talked about the block sizes, and it could be advantageous to design around that size, including, actual height of the wall and spacing of your horizontal bars. Is there any discussions in like ICFMA or anything to standardize those? So when we do a school, it's got to be competitively bid. We may not know who's going to be doing it. So it becomes difficult to tailor a design to 3 different manufacturers if they're all doing different things. Is there any?
So an example is Huckabee Architects, and across the country in the educational sector, it's 90% Rebar. So that's an 18 versus a 16. So that's the lion's share of the market. Right. So the outlets are the same, concrete pour size is the same, and on the structural pages, there's a call-out box like this. It shows 18-inch on center horizontals for that brand, and it shows 16-inch on center horizontals for that brand. So that's the way. You're not going to be able to get away with. There's about a dozen manufacturers that have 16 on center. There's 1 at 18, 2 at 12, and 1 at 20. So 90% of the brands are the 16 on center, but you can always do a call-out box.
There's enough that it could be competitive bid.
Always. Yeah, it's a bloodbath out there. I never did it for that.
But isn't ICF a means and methods anyway? So it's not really a product per se. It's just a form material.
Well, 031119 ICF spec, CSI spec. You're always into the part 2 products. We always see our competitors or ourselves called out as basis of design, and then allowable other. So, yeah, ICF is a means and methods to cast in place concrete walls, but there's code approval reports specific to each brand and different logistics, manufacturing locations, some other factors that come into play. Yeah. Not to be trusted, but we're saying, guys, if you really want to trust Steve, help him. And Steve, raise your hand once again.
Yeah.
He's got, so I want you guys to look for the big fella because he's going to be leading us. And please, he's got some great tips, tricks. Please take him up on all that. And I would like a quick show of hands, like from Clark. How long have you guys been building with ICF?
The 80s.
So, a wealth of experience. Anybody else with a lot of experience? Robert, how long have you been designing ICF?
Only ICFs for 16 years.
Only ICF for 16 years. Remarkable.
Architect?
Yeah.
What state?
Arizona.
But he's all over. So, and Mike?
I have no idea.
So, you've got huge resources here. Please make use of them, and we're sure glad you can. We're going to head next.
So, hey, quick question.
Yeah.
Since Arizona is so big, you mentioned earlier, I think it was you, that the energy savings is really almost non-existent in the warm climates, but when you get into the super hot climates like Arizona, does energy now become a big deal again?
Yes.
It's huge.
Yeah.
So it's more of the temperate climates that it's not.
Yeah, if we're on Laguna Beach and it's gonna be 65 degrees,
Yeah, it's not a big deal.
it's not gonna make, we get projects there for other reasons, just lower cost, faster consuming.
So I would think real hot communities are even bigger savings because you're electric on cooling, a lot of times you're electric, so.
Actually, it's the reverse. The ICF efficiency, so the national average is 46% energy savings. It's actually 41 on cooling, but it's higher on heating savings. So those two combined bring it down. So really, really good for cold weather climates, really, really good for hot weather climates, but the cold weather climates enjoy just a skosh more savings. And the core is already out, and there's a hole there for this one. And he's holding this apple, and he tries to pick up the core, and I thought, no way is he going to be able to do that. And he did. I was astounded. So it's just, rather than having the concrete hole saw guy come out, it's fairly easy to take a PVC pipe, the length of the wall, and at the width that you need, and actually cut a hole in the foam, and cut a hole in the foam on the other side, and sleeve that pipe in, and then pour it.